microphone, there's only one because there was a difference with the label. Only one. Okay, thank you very much for coming. We will start the event briefly. We are accepting the last people online to connect. How many people are connected already? 26 people already connected. 96. Opa. There's people online. Pressure, pressure. But since we have excellent students that have been presenting, that will come to present amazing work. Ah, wow, already silence. We have a full support, video support on the back, and online connection. Are you ready to start? Yeah? Great. So we'll start with an introduction by our dear Edouard Cabet.
Thanks, Alex. Thanks, thanks everyone, both of you that are here physically, those of you that are also online. I think we have a good afternoon, evening coming. So this is the fifth edition of the Open Thesis Fabrication, in which we've decided to take this focus into 3D printing with Earth. OTF, 3DPA, we are changing the name actually of the program to 3D Printing Architecture. So hopefully in the future, you'll hear more about this 3DPA. What do? We look at the potential of 3D printing with Earth. 3D printing, I think it makes little doubt that it's a technology that is going to be very present in the future of construction. It's going to change the way things are built, but as a consequence, it's also going to change the way that that we design, potentially think about space, and definitely going to change also the way that we live. No? These are some of the questions that we're exploring in the program. And Earth, well, Earth is a material. Maybe in the beginning it was our testing material, but little by little we've grown into believing that it's a really good material for this technology, despite the possible kind of contradiction that there might be between a cutting edge technology and a material that in the construction sector in history has often been kind of associated with with poor architecture. No? But earthen architecture exists all over the world since always. It's been a lot replaced by concrete, but still today there is a lot of earthen building around the world. And it has a lot of properties that are very positive that we're going to be seeing throughout the day. But at the same time, it's a material that is really interesting for us because we can find it under our feet, right? Clay exists, earth exists in every country in the world, in every region, in every village, potentially in every construction site. And there is something different about constructing with something that you find directly under your feet. That doesn't necessitate a huge amount of production, that doesn't need a huge amount of energy, that is a material that can be clean, recyclable. It has many advantages, but maybe the most important is the fact that it is locally sourced, right? And that has a lot of consequence. And these are the questions we've been exploring. So the program is a 6-month-long program that is concluding today. We've been working with 11 researchers or students that you're going to meet today. I think you're from 11 different countries as well. And we've developed the program into three phases this year. The first one, which was a 6-month-long exercise, was developed as a collaboration with l'Association de Ceramistas de la Bisbal, which is a group of ceramists that came to us to develop a piece of research for the Biennale of Ceramic that happened back in November in La Bisbal. And so we took that as a kind of ground in order to go with the students through a 6-week research in which we went through all the process of the work. So at the beginning, we started to build our printers. Then very quickly, we got familiar with the material with Elisabetta here, which we're going to introduce in more detail in a moment. So developing understanding the material, developing certain mixes. Then we looked into the structure of 3D printing with Guillaume Baraut. We looked into aspects of design, how to design. In this case, it was a column that was also a chimney at the same time. You'll see more of that on the screen in a moment. We looked at the design process of how to design for this technology. And then afterwards, we went through the production. So the students all together actually did a small, let's say a small building site here in the back and constructed this object, which was afterwards brought to La Bisbal and fired on site during the time of the Biennale. So that's for us a kind of 6-week, very intense phase in which we go through the full process. Technology, design, performance, but also construction, and then eventually performance in this case. So that's the first part of the program. Then afterwards, we go into a phase that we called the research. So the research is something that is directed by Alex and by Kunal, who is here, Kunal Chada, who is our fabrication expert in the program. So for a length of 3 months, the students work in group and they take a question. They look at state of the art in the field of 3D printing with clay, and they ask themselves a question, which then, with a kind of scientific methodology, they test, they prototype a lot, and they eventually come up with some solutions, one of them being some of the prototypes that you see around us. After that, we go into the last phase of the program that is a couple of months long, which is the studio, in which with the same group, actually the students then speculate on an architectural proposal. So rich of a very good learning that they've done in the research, they are kind of really trained into how the technology materiality works, and they are able to start to attack also design questions. So this is something that studio that I was running myself with the help of Ashkan, who is our faculty assistant and also has been actually involved through the whole length of the process. So you're going to see a lot of him through all of the prototypes. And that last phase of the studio emerges also with some images of kind of a perspective idea of what 3D printing with Earth can propose as a domestic architecture. Yeah, we're going to see a lot later, and I'm curious to see what kind of conversation and discussion we're going to have. So before we start, Alex, I pass you the mic so you can tell us a bit more and introduce our guests.
Thank you very much for this introduction. So 3-phase exploration. we'll have a video we'll present right now, 4 projects of research, and then break, and 4 projects of studio for this evening. That will hopefully trigger very nice discussions, and we are hoping to be provocative and looking at our jury to challenge a bit these architectures, this design, to understand what this is actually bringing. One thing we'll ask you is to be clement with the student about the challenge of 3D printing with Earth on site. That is, let's say, a given, something an assumption we put on the table that the student have to be around. So we believe there's a lot of potential with this. Let's focus on their proposal in this context of proposing amazing architectures. It's not an easy context, but we believe one with a lot of potential. Today, we have in the jury the chance to have the faculties that have been assisting the students in this evolution. So we have Elisabetta Carnavale, that is also an architect with a lot of experience with Earth architectures, but I've been teaching them the tricks of the matters. We have Guillaume Barrault, that is engineer at BAC, collaborating with us in these programs, and have been trying to find with us design tools to be able to deal with structures without having to go for the full simulation with structures. So we're inventing a bit all of our tools. Evidently, Ashkan and Kunal that have been extremely supportive during these 6 months. We should have Eduardo Chamorro that is connected online, but unfortunately was traveling, so couldn't join directly, but I think would be nice. Angelos. Yeah, it's possible. Yeah, it's possible for work. Angelos, that is also remote from Greece. Angelos Kronis have been amazing. But today we focus also on our physical and external guests, let's say. So we are very happy to have Silvia Brandi, that have been a long supporter of the project, now working at Atlas of the Futures, architect by formations, and now visionary, exploring what solutions could make a better world. So very much thank you to join us. Ana Ramos, that have got a special feeling for understanding what architecture could bring to our society. You're leading also the Semana de la Arquitectura in Barcelona and the Foundation Miss Vandero, so very iconic. We're very glad you came to see here. No pressure for students. Areti Markopoulou, that is our academic directors, but also amazing talents in research that have been developing in EAC for the past 15 years. Don't be too critic on the words, but that's nice to have you. And Grégoire Durins, that have been a long-time follower of what could we do between ecological constructions and fabrication laboratories and technologies that we have here. Now you're working for the past 10 years for the Earthship constructions, and you're trying to look at how technologies could rethink the way we print or make these constructions. Always critic with our work, but also full of ideas. Some of these projects also directly speaking to your research. So really looking forward to your comments. We will have also joining us a bit later, Joseph Ferrando, that also should have a very good critics on our works. And we have the chance to have our only online jury guest, Lapo Nabolny, that work at WASP, developing computational design there, and that represents all the support that we have from this company that is collaborating with us. Thank you so much for joining us online. So we're quite excited for this afternoon, and we don't speak tomorrow. We'll start with a small video of this first exploration we've done in just 6 weeks with a student, so kind of a sprint from 0 to 100.
Firing completes the transformation of clay from a fragile material to one that is resistant and impervious to water and time. Can a building be fired? Can an object be its own kiln? Phoenix is an experiment examining how 3D printing allows the development of an architecture built with earth that can be fired to improve its resistance and durability. The initial geometry is defined by two layers that create a continuous cavity within the structure. An external shell is added to guarantee that the internal wall is encapsulated with heat. For the firing process, torches are positioned at the bottom of the structure. The airflow produced by the flames appears as the first gesture that determines the connection between the two walls. The orientation, size, and position of the connections influence the dispersion of heat throughout the walls. In addition, the inside wall is drawn with openings at the bottom to allow heating of the interior of the structure. From the connection in two dimensions, a landscape is created and later projected onto the original geometry. The inner wall becomes the final chimney, while the outer shell is designed to be sacrificed. The continuous cavity is designed to guarantee stability, geometric union, and homogeneous distribution of heat. Clay is mixed with additives to increase its structural performance, ease of printing, and to aid with the firing process. For fabrication and ease of transportation, the structure is divided into 4 pieces of the same weight. The work of design, prototyping, and production leads to the final assembly on site. The 4 separate parts are precisely put together to compose one single object. Torches are lit at the base of Phoenix for the beginning of the firing process that lasts more than 15 hours and reaches 1,200 degrees Celsius. Fragments of the outer layer are carefully removed and collected, exposing vitrified interior elements. At last, the moment of discovery, revealing the architecture within for the very first time.
Okay, this was just a glimpse of what we propose in this program, that is looking at performance to drive our design, understanding the materials, the machine, the complexity of these systems in a very specific case, because we are looking here at how to cook the earth and make it more ceramic-like. That is a big challenge, normally requires a huge oven. So that was a strange experiment, but who knows, maybe once it will be scaled at the scale of architectures. Now we will look at other type of approach of how to deal with heat in a construction made of earth, and how the design possibility offered by 3D printing will bring new type of typologies and efficiency. So I'll invite you to join us for this presentation. We will start a first analysis or first project of research about heat. If I find the right window. Please come in. Your turn.
Good evening, everybody. My name is Timur. This is TK and Roshin. Today we are going to talk about heat distribution in 3D printing architecture. And the title of our research is 878. Fire. From the beginning of the finding out the fire was the prime source of the heating in our buildings, and architecture and fire played a major role in construction of the building. And here comes the question: can a clay 2D printing improve heat distribution mechanism for sustainable thermal performance? Or how the conscious design of cavity and mass in 3D printed wall can upgrade a sustainable heating demand? Here you can see our abstract of our research, but shortly it can be described as a theories and principles of thermodynamics and 3D printing architecture using clay. Here is the concept of our research. On the left, you can see a conventional fireplace, which heats the space indoor, but a lot of gases and heat flow goes outside. It's not very effective. Well, what we would like to offer, it's a 3D printed architecture fireplace, which has a controlled cavity with heat flow, and we can simultaneously heat the wall and the space inside of the building. Another idea of our research is to control the heat source. So we can turn on the heat source for a certain time. We heat the wall through the cavity. After that, we turn on the heat source, and the wall itself passively can heat the space in the building, providing comfortable environment. We started our research based on these references. The first is the Phoenix. You saw it in the video in the beginning. The second reference is a ramped earth stove made by Martin Rauch. And the third one is Russian masonry heaters. And we took idea from there about better harvesting of the heat and how to use the heat transfer in the best way in the oven. Components of the usual 3D printed wall consist of the cavities, and we can use them for insulation, for thermal mass, and to control the heat flow. Here you can see a geometry exploration we took in our research, and there were two variables about a cavity, and we explored cavity from the point of view of heat distribution, and also from the point of view surface area between mass and the cavity of the heat flow. Another variable was about the mass itself, amount of mass we can use, and the surface area of the mass. Here you can see design iterations, 4 design iterations. It's about a cavity iteration, about surface area between mass and cavity, about mass itself, and about surface area of the mass, which heats the space. Here you can see all the catalog of our iterations we developed during our research. And on the next slide, you can see examples of these prototypes, and you can see different surface area of these prototypes, which can provide a different heating, time lag of the heating of the wall through the space in our building. We used different methodologies. First one is a computational analysis about simulation of the temperature inside of the wall. Another is a digital analysis for transmittance value, and we finished it by physical thermal analysis with a thermal box we developed and using thermal camera. Here is an example of computational analysis of transmittance heat through the clay wall. Here you can see workflow of our research. So first step is to create a prototype with a 3D printer. Then we filled the cavity with a mass. We used the clay powder. We compacted it with stone. Then we fired it with a gas. And we tested this prototype in a thermal box. We measured temperature inside of the box and outside with thermal camera simultaneously.
So as he said before, in order to perform the physical test, we have designed a thermal box. So a thermal box is containing a Arduino kit that is used to measure the interior temperature, and it's insulated from the exterior. And also we have a live simulation that give what is the temperature inside and from the exterior of the mass that we have inside the box. So this is how we evaluate the result from the thermal box and the camera that we have incorporated in the design. So talking about the digital analysis, we did the computational fluid analysis and we compared with the physical test. So this is a simply extruded model with the heat is at one point and it's directly evaporating, getting outside. So the heat is not transferring from one point to the other point and it's not heating uniformly. So then we modify the geometry and we can understand that we have a heat source and the S source at the another extreme point. So here the mass is the cavity that create the heat to transfer from one point to another point. So we can see the temperature is reaching around 62 and before it's only 29. So the cavity help for a uniform heating. So further study, we try to take the section of our physical model so we can understand what is the comparison of the CFD and the physical test. So since the CFD is the main our research methodology. So then we evaluated our results with the diagrammatic way, the live simulation result, and with the digital method. So here we try to understand what is thermal capacity of the mass in physically as well as using digital method. And as an overall result of our research, we can show the performance could be enhanced by altering the thermal mass and the surface area of exposure. So then keeping the mass constant, we try to play with a different iteration on the base curve so we can harness more surface area, and it is used for better heat performance. So before we start the prototype, we have concluded as a research is a 3D printed wall cavity for distribution of heat helps for better indoor heating for enhanced sustainable use of resources.
So after we have studied all this, what you have seen, then we managed to propose a 6 meter by 4 meter wall for our prototype design, and doing that in 1:5 scale, and which yields around a rectangular shape of 80 by 1200. So the idea is that first we try to anticipate what kind of heat do we want to channel through. Based on our area of exposure, we tried different alternatives. Then afterwards, from our previous studies of the Russian mass heaters, we can able to achieve a bell, the concept of bell, which means containing the heat for a longer, for a better time lag of containing the heat for a given purpose, and channel the relation between the bell and the channel. So adding these two would have given us the different iterations of different channels that we can try on our wall. So we take this advantage of the final line, this one, then offsetting this as the areas of the exposure gives us. We will have an offset. Then on the axis FF, you can see that we have a bell created, the bell meaning a volume of cavity that we can enhance for a better radiation of heat. So after this, we try to understand what kind of structure do we need to support this cavity that we want our heat line to follow through. So we need to understand the structures. We zoom into one single module and understand the different characters of the structure, how much we can achieve by doing some structural adjustments. And also you can see with the additional of introduction of both legs, as you can see here. So finally, this sum would give us a geometrical approach, which you can follow the line, and also the incorporation of the bell on the top side, the section, you can see it. We have a more space that we created. So that integrating the heat source, as we can see there, we can have, for example, you can take this wall, can radiate based on the needs of the change in surface area, and the more mass we have around the surface area by the research that we have done before. Then after the 5 days have been, we took 5 days to produce this thing, and it's around 400 kilograms of clay. Then this is the elevation of the thing that is generated through only the line that you saw based on that heat line performance, which can be anything when you assume of an architecture. So a nice output of this, how we can prove that our idea is that the more surface area and the more created bale we have is there. So this is the total time lapse, as you can see. On the first we have yellowish. On the second, this is around 20 minutes on the heat source is on, then you can see the more radiates the thing. Zooming into the micro textures, you can see the different textures that we have on the intersection. The more intersections we have, the more mass we designed it to have in our form. So these are the different thermal imagery after we test the building.
So as a conclusion, we are looking, is the efficiency of 3D printing wall able to replace the conventional wall for sustainable application of thermal mass in passive house design? I lost it. Okay, so this is a video. Yeah, it's very nice.
So as you can see here, this is the full elevation of the thing, but from the top, you can see the cavity and the bell from the next videos that we have on the topmost view. There you can see the bell that we were talking about to contain more heat, to create the lag of thing based on our safety simulations. And we printed in two different levels so that we can have the full structural strength of this idea. So based on our heat source, we map our thing and fire it at the end, and you can see the temperature difference really increasing around the cavity that we created, which is really big, and the specific heat capacity of the clay, which is 787, sorry, is we can really use it to have a nice indoor comfort conditions. Thank you.
And also before presentation, we heated our wall. This is our prototype for 5 minutes. And here is a real thermal image. So the heat source is turned off, but still you can see the heat distribution through thermal camera. So if you're curious, you can look at it later.
Can we touch it?
Yes, sure.
Actually, welcome to touch this one and also to see that on the. Welcome to come closer to see the prototype here, and also on the back, you have some of the sample the students have been producing at small scale. And then who wants to start to comment on this work is welcome.
When did you heat it?
It was like 20 minutes before presentation. We heated it for 5 minutes. So, and it still radiates the heat after 1 hour. With a gas torch. On the right, you can see the gas balloon and the torch.
And for better, the infill material, we didn't mention that. You can see that there is an infill material, which is chamota, that we use, we compacted inside so that it can contain the heat. Then it radiates when we don't have a heat source.
Maybe to help quickly our juries, this is the first phase where we look in the technique of the constructions and all the details. And the second phase, we look at more applications. So what can we use this, how we can use this into constructing a different type of architectures. Who would like to jump? Go for it. Thank you for breaking the ice.
Yeah, because I'm excited. I wanted to share. So thank you. Well, thank you for the invitation to participate to this jury, and thank you for your presentation. I mean, it has been super clear, super lovely, efficient. So very nicely delivered, and that I'm very impressed by the project. So I have the sensation, like imagine that we are in 2021 and someone just invented the door. Looks like you just invented a new element of architecture. So now with this is like you just killed the fireplace for the firewall, I don't know, call it whatever. I mean, you just invented, so in 2021, we just invented a new element in the architecture, which I think is amazing. So that's what I'm fascinated. You reinvented the fireplace with something totally new and incredible. So that's not easy to do, obviously. So congratulations, because you totally demonstrated that is working, is a brilliant idea. It's like taking the radiator and put it at the scale of a wall. Very, very nicely thought and developed. I have just one doubt, of course. So which source, so you are imagining, which source of heat are you imagining? So it is like fire with the, like wood, firewood? Because this is one of the most contaminating thing in the world. So maybe we should check out this. Now, you know that the burning fire is releasing particles that are much more contaminating than the car and everything else. That's why they are banned almost everywhere. So can this idea, which is brilliant, be applied to a source of heat that maybe is the sun, which would be change totally the project, or some other source of heat that is not burning, which is, as you know, not good because of the contamination, and not good also because you are degrading a material, which is wood, to energy, whereas you should use materials for material and renewable for energy. But the firewood is not totally sustainable as no, to pass from a material to energy. So do you want to answer? Okay, great. That's a start.
Okay, so we just used for our prototype, we just used gas just for conveniency, but like 40% of the current single unit house in the world have fireplaces. So the idea is, like, if we have this immense number of fireplaces, why don't we try to use to think about how to use it sustainably, so that previously, as my colleague mentioned, we burn the wood and immediately we feel the heat and the smoke radiates. But what if we channel it around? That's the idea we had when we first anticipate. But in order to show here, we don't need these things. So for conveniency, we use this. Maybe in our future, in our next presentation, we have something related to architecture, how this could be applied in architecture. And I think we can have a say there.
Another important thing to mention that we also derived idea from Russian masonry heaters and from rocket stove. What does it mean? With using this bell, we can mostly fire all the combustion gases inside of the wall. So most of the smoke will not go outside to the atmosphere to pollute it, but most of the heat and most of the gases will be again heated and transformed in our wall, and it makes it 90% more efficient than usual fireplace. Yeah, no, we read about it, yes.
Yeah, thank you very much, and thank the organizer for inviting us here, first of all, and congratulations for the presentation, because I've seen your whole evolution through the whole course, and it's really impressive. I just want to start with a very simple question. It's very simple. So why just a wall? Yeah, just a quick answer. The second question will be more difficult.
Maybe I don't want to answer. It's just the prototype. It could be anything.
Don't be scared. Okay. No, I mean, for me, the correct answer, because we discussed this in many sessions. No, I understand that you need to do very simple experiments to understand the performance. Okay, so I agree that just a wall works to understand how the heat is being distributed and so on. So from that point of view, I understand that you just built a wall. But the good thing is that you're in a 3D printing course, and in 3D printing you can print whatever geometry you want. So if we go back to the very beginning of your experiment, which is heating a space, heating a living space or whatever, I mean, the problem that you have in any fireplace is that you cannot have a fireplace in every corner. But what you want is to have kind of the most uniform heat you can in the whole space. So doing the experiment in just a wall, for me, is probably a bit too much simple. That from one hand, as I told you before, is good to understand the behavior. But my critique would be, okay, you already did that experiment with the Phoenix project in 6 weeks. So after the 6-week project that you understood how to distribute the heat around the chimney, I think that maybe I see a lack of going a bit more ahead and trying to build a 3D wall, whatever, a 3D space that is able to distribute the heat all around the space. Because I mean, in a certain way, and this is the negative point, but I mean, I'm really happy to see the results. This is kind of a second or third iteration of the same experiment of the Phoenix. And I would even say that even with the Phoenix, you achieved a much uniform distribution of heat around the chimney. So I would be really happy to see a bit more complex geometry that is able to distribute from a single source of heat, to distribute this heat all around a much complex space. And 3D printing allows you to do that. So any thoughts for further experiments, let's say?
Will not burn, huh? Don't worry.
Okay. Okay, I will try. I will try. Actually, it's not an answer, but of course, we can integrate this idea for, of course, 3D printing will allow us to discover many unreachable and untouchable imaginations that we cannot imagine before. But the idea is, as you said, to simplify it and try to disintegrate as many variables as much as we have. But the main thing is we can incorporate this thing in every of these projects, actually. I agree with that totally. We can incorporate it in a window. We can incorporate this in the cavity. So we can channel our buildings with the uniform heating. But the idea is the first assumptions that we started the prototype project was, okay, let's just zoom in so that we can, this was the decisions that we made. Yeah.
In their favor, we've been insisting to keep it simple because the number of formulas that they pull out before being able to reach architectures was quite long. There was actually an amazing scientific work to try to understand the dynamics at plays, and each time we ask experts in what is the fluids and how the smoke move inside and how you transmit the heat, is mostly the experts say they are more or less understanding which direction it goes, but there's not a common knowledge, no? And it's quite difficult to grasp and to understand. But actually here we can have Grégoire that will tell us about his own experience with rocket stoves recently. Tell us.
Thanks, Alex. First of all, congratulations for your very good scientific work. I found that was amazing, even though presentation is of course very short only. So it was very fast, and as a physics enthusiast, I'm trying to follow, and it's too much to absorb, but it's not your fault. And still, it demonstrated a very good scientific work. And from what I understand, we're going to see later how that could be applied to something else. So I'm gonna stick to the scientific work that you've done. I almost think that it's a very good validation method of the physical model of how heat works that you've done here. That you're almost trying to demonstrate that the physical model of heat distribution that we have, that's always has some sort of inaccuracy, you're almost trying to help make the physical model of heat distribution better. And especially with Earth, there is not so uniform data on how Earth mixes are behaving with heat. And with that level of control on the geometry and everything, you can really push further the theory of heat distribution with Earth. And that, I think that's very nice. As Alex said, recently I've been building rocket stoves, and recently we've been designing a massive rocket heater based on the latest findings. So it's called the batch block because it works in batches. So you must know, but that's because we use wood to make sure the burning process is very efficient. We do it in batches. So we burn everything in 20 minutes so that it reaches a high temperature. And then slowly with thermal mass, it distributes that heat wherever we want throughout time. The main difficulty that we have is to size what we call the ISA, the internal surface area, which is the size of the bell. Because one of the critical things about any stove actually is to make sure that the temperature of the output fumes are neither too hot, which means we lost energy, or too cold, because that means we have a draft problem. and that can cause condensation as well. What I really like about this research is that you have total control on the design of the surface area of the bell. And you can, throughout many prototypes, find out what is the optimum. And that's what the community of masonry, rocket mass heaters, builders are finding today. They have a difficulty finding an optimum. And it's kind of like, it's not random, but they just like trying things out and say, yeah, that works better than this one. So they're doing it empirically, not scientifically. And I think that's a very good way to actually say, this is the internal surface area that's best for getting this this output temperature, which guarantees a good draft and no condensation. And yeah, so that was just comments. Then I have a question, but that's kind of linking with the application of that in terms of housing, which is less related to research. But yeah, it's for architecture, for like case studies in architecture. My question is, isn't it a little bit too complex compared to just having a mass that embeds heat and releases it slowly? I mean, that has not been invented recently. Like, I think about the hypocaust in the Roman times, which was that in the ground, for example. So this is not something new, and I'm just asking myself, what is the trade-off of complexity that we want to find so that there is performance and at the same time not too much complications to build. So that's also linking with the other presentation on applied cases later.
A very quick comment just to add to everything that has been said. From my side as well, congratulations. Thank you also for the great introduction to Alex and Eduard, but also to the rigorous way that you have managed to present the work. I kept on thinking on one thing that has to do with the fact that, you know, like we see a wall, but the value of that wall is actually where we cannot see, no? And this intrigues me a lot, you know, like the fact that there is a lot of design sophistication and a lot of design experimentation in the inner part of that wall where you actually cannot perceive it, no? And I'm saying that because on the one hand, this could be interesting because it's the hidden power of architect, scientist, and a manufacturer, or it could eventually become a kind of an input that would reflect or that could reflect into the aesthetics of the piece, no? And I think this is something, I'm not sure if you will talk about it later into the application during your research, but I think I kind of find a pity the fact that, you know, like it is very little represented what is happening in there in terms of complexity into the outer surface. And I wonder, whereas if the outdoor surface would somehow follow that optimized design of curves and belts, of cavities and belts, whereas this could even more optimize the performance of that wall. Because at the end of the day, what you want is to distribute heat also outside in the room, no? And the experiment that you have done with the box is only testing the inner temperature, no? Or have you also tested? You also test, okay. And then how many cavity and belt iterations you have done? Because I think this is important, no? In your presentation, it felt like you only had 2, but because I've seen that there are different models, I think that this is also very important because it is a kind of a continuous exploration on really achieving an optimum form. And I think that this is important to somehow, yeah, showcase it. And it's so important, that's why I say that it even works, you know, to become a kind of a projection to the surface as well, not just height in the interior of the wall.
Can I just, sorry, I have one more question, inspired by Areti. So this pattern you have on the surface is functional or is aesthetic? It's functional. So you need to have, so this is because you have an interior cavity in that point, like a radiator, yeah. So it's to augment the surface. Mm. Ah. Mm-hmm, yeah. To augment the surface in this surface. Yeah. Mm-hmm.
I want to talk. Yeah, I precisely wanted to congratulate you for the beauty of having, the function, both not only thermal function, but I will also refer to the structural function. Because if you're aiming to create a wall 6 meter long, 4 meter tall, you will need these vertical changes in geometry. So, you have created this element which is purely following the physics, both in terms of gravity or stability or thermal behavior, but you have created this beautiful texture also because clay, 3D printing in clay, it's so beautiful because it creates this texture of lines that is so inspiring. But then by adding these vertical lines and then doubling the space in the areas where the heat is, that already creates a vibration. So it's super interesting. My only thing is, again, what you stayed there in these two lines. So you would probably, the first step would be probably to start thinking of having, fatter parts of the wall and thinner parts of the wall. So start having some movement towards having a more beautiful stove. If still, this is kind of a huge stove. And then the next, if I have to answer the question to my colleague about how could we create the whole space about this, I was just this morning teaching my first year students in architecture school precisely about the earth, well, the ceramic domes back in Jericho times, in Mesopotamia, which was kind of almost the first way of, in Neolithic times, of how to build these earth domes with the fireplace in the middle. That was kind of super efficient. So probably thinking of some spiral issues, you could create kind of spaces to be inside the stove. Yeah, but I really congratulate you and the whole workshop, because it's very inspiring the way you're mixing physics and beauty. Yeah, so congrats.
I also really want to congratulate you because I think the project is brilliant, and I also want to congratulate the faculty of the OTF because I can clearly see from 1 year to the next, really the quality of the project, the coherence of the project is really growing. So it's getting really very, very interesting. I think what you have there is very interesting, following different aspects. First of all, as an architect myself, I struggle a lot to find heating devices that are visually interesting, that have a visual quality. This is really rare. We tend to think of, I think Edward knows about it. We tend to think of heating and installation in general and pipes as something that is separated from architecture. And we really need to start thinking of it as something integrated. And secondly, another thing that we miss in our heating devices is the touch. It is a very basic sensation, and it is a very beautiful way to experience architecture. And we normally don't have it. We can't touch our heating systems. It just happens for radiant floor and radiant walls, but it's an exception. All of the other systems, they don't allow us to have this nice feeling, and here you have it, and I think it is really enhancing the quality of this device. Well, parentheses, as a material expert, I really appreciate that you put some feeling inside. I think it's great. I wouldn't use chamoto because it's a very porous material. I would try to search for some denser material. I would use sand or earth that would have bring the advantage that it would regulate the moist even more in the indoor climate. End of the parenthesis about materials. I think from an architectural point of view, I would definitely try to think what is the B side of it, right? Because now we have this side, we see what is going on here, but definitely if I would integrate this into an architectural design, I would have it separating two spaces. So what happens to the other space? Am I also able to hit that? And how is this interaction going on? And I definitely think my colleagues have a point, Guillaume, who was talking about how to integrate this, not just into a wall, which is of course the first thing, the basic, but thinking of it as a system. And here, I think we are really touching one of the the strongest point of 3D printing architecture, which is thinking of the wall as a system, as a way to really answer a lot of questions at a time. And I think here is also the answer to what Gregor was saying about the fact that this is really complex to be a heating system. I agree, but what if this is a wall that is a heating system and has all of the other questions solved within one element? Then it starts making a lot of sense. And of course, having a different geometry could be very interesting. I would like to know what, for instance, Lapo would think of this. If you think of this Tekla prototype space where you can have heating all around you and really use very efficiently the heat that you generate until the very last bit of energy. So yeah, well done. Oh, good. Let's have the answer live.
Can I speak? Okay. Hello, everybody. Hello. Congratulations, guys, for your work, and thank you. You made a very beautiful scientific research. And first of all, I have a question for you. What do you think about the extruder that you use to create the mock-up?
Promotion.
Because I have to decide which is my question. No? So I want to see. I want to know.
Sorry, can you repeat, please?
Ask if you like the It's amazing.
Yes, it's amazing.
Okay. No, I think that to embed multiple functions inside the wall is one of the most biggest challenge of 3D printing, and it is one of the biggest quality of 3D printing, you know, because now we live in a world with architecture with multiple shell of material. And in your case, you embed multiple functions inside a wall. So I think that this is one of the best things that we could do with the 3D printing in architecture. I have only one question, more technical. So today I'm an engineer and not an architect, and is related to the differential shrinkage, because you are heating soil. So I think in my experience that when you use paste based on soil, is impossible to have a shrinkage. And in your case, you have differential heating along the wall. So I think that it's possible to see differential movement of the wall and the possibility of cracking. Have you seen something like this in your tests?
Actually, it depends on the power of the fire. We didn't use I don't know, like 1000 degrees of the heat source. It was much smaller. Some of the prototypes were cracking, but yeah, it depends on the thickness of the wall and is it very dry. With the final prototype, we didn't have any cracks due to heating. It was fine. Yes.
Thank you.
Thank you. Yeah, the problem is that actually normally we have 10-minute comments, and we for the first round it was good to have more half an hour, but we'll have to accelerate. If you have more comments, we're happy to share it, and the student is super available to discuss for an hour. But to make the event a bit more dense, we shrink a bit. That's why the group of the light will join us now to speak about also their research about how to deal with this very important physics in building, light. So please join us on stage.
Good afternoon, everyone, and welcome to our presentation. We are Tapiwa, Luis, and Lynette, and our research topic is in light. And to this end, we ask the research question: how can we 3D print clay to create lightness with illuminance in architecture to have performative qualities according to a given climate? We were interested in two conditions of light, namely diffused light and direct light. And we defined diffused light as soft, evenly distributed light that eliminates harsh shadows and glare. And we defined direct light as high contrast focused rays of light that create harsh shadows and glare.
So we had a methodology to find this optimized form of light conditions, these two light conditions. Firstly, trying to understand what diffused light actually is like in terms of a qualitative experience, and then trying to find out what printing scale that we can use in order to create the optimum openings. Then looking again at opening types to see what type of openings can be printed using 3D printed architecture, clay rather. And looking at different references, then exploring different geometries and designs in order to finally test our model digitally as well as physically for these conditions to create this hybrid performative light. Since clay is a material that works best in compression, creating openings was one of the big challenges, which is why structure is going to be a big part of what we were exploring. We looked at a couple of references where you have direct lights by Louis Barragan, where you have diffused lights, and where you have the Jali, which actually operates as a, in terms of cooling air in the depth to width ratio of the opening.
Because we were interested in light, we selected the small scale of openings as a representation of the type of opening that would be able to be responsive to allow in light into a space, but to also function with regards to air movement.
So the issue, as we said, with trying to create an opening in a compressive material was the fact that the clay does not want to perform in this way. So actually finding a printable structure was one of our biggest challenges. And eventually we got to a circular or round form, which seemed to be the most structurally stable.
Yeah, so as Tapiwa mentioned, this is one of our first iterations that we tested. By starting with this print, we realized that by slendering the geometry, we were compromising the structural stability of the piece. So we have to switch to a different strategy. This is a quick summary of the catalog of iterations that we did. Basically, what we are explaining here is the digital analysis, either a global inertia analysis or inclination analysis. And what we are extracting from these tests is the amount of percentage that, the opening percentage, and also the percentage of mass. So the first test that we did was the diameter of the element. By modeling the geometries, we then we tested the global inertia of these elements, and then we filtered this into the elements that we were going to test print. And then by just looking at these elements, we decided which geometry we were going to use. Then the next test that we did was the cantilever in X direction. And by testing the amount of inclination, we did the same process. So we filtered the successful geometries. And of course, first we had to select the most stressed geometries. And then we printed it, and we conclude that the number 8 in this case is the ideal. The next test we did was the connection between the elements. We ran them through the analysis of global inertia, and we selected number 4. So the last test we did was cantilever in Y direction, where we tested global inertia and also the inclination. Then, well, what we were looking for is having a more stable diffuse light. We wanted to increase the section and to have the, let's say that these are the different strategies that we use to increase the structural stability of the piece.
So in order to test the qualitative and quantitative aspects of light, we made an experimental setup where we had a camera set up at the top and at the bottom, and we would put our geometry inside this black box and take photos of the light that we would have. We also had a lux meter on the inside to test the amount of light that was actually going into the space. And we used Barcelona, or we use Barcelona as an example of the different lighting conditions that you could get. So for example, at 3 p.m. when the sun is super high, you know, would be a different lighting condition to what you would want in the morning at 9 a.m., for example. So this just sort of emphasizes the impact of inclination and how the impact of the inclination of the sun has an effect on whether you want diffused or whether you want direct light. So this is what some of the results that we got, where we were able to see that by having more layers behind in our wall, we were able to then diffuse light, which was what we were starting to get at towards the end. Initially, when you have few layers, you essentially get direct light that moves straight into the geometry. So as a result, this is what we sort of started to explore, which was how many layers of these clay printed walls can we use in order to have direct light and diffuse light. What we managed to achieve was based on different positions or based on these different angles of the sun and the desire of light that you want, we were able to print a geometry that appeared to be more open and had more openings on one part and had more diffuse light and less, the impression of smaller or fewer openings from a different perspective. So after understanding that we need a number of layers in order to create diffused light, and also understanding that we don't need as many layers per se in order to create direct light, we started to, we identified 2 points, point A and point B, one which we wanted to have direct light, and a point where we wanted to have diffused light. So again, paralleling it to the fact that at a certain time in the day when the sun is harsh, you want diffuse light, and at a certain point, you probably want direct light, like in the winter, for example. We were also interested in the slenderness of the elements that we were printing. So we wanted to make it as thin as possible and to see, you know, sort of how much of a lattice structure we can create with our geometry. And this was essentially where the point that we got to, which was just understanding that with fewer layers, you get more direct light, and with more layers, you get more diffuse light. However, we had another layer of understanding this, which was that if you have light coming in from point A, let's say point A is the morning, and you have light coming in and it's direct light. When you move to point B, which is the afternoon, based on drawing the paths of light, you would be able to diffuse the light, which is what we wanted to be able to achieve. We also increased the mass of our wall in order to take advantage as well of the fact that the clay can have, we can use thermal mass as an additive performative quality. So we achieved light, diffused and direct, privacy in terms of, you know, the opening types where you can see all the way through or you do not, and as well as cooled air through the proportion of the openings to the depth, and a wall that also can produce warmth through passive solar heating. And quite simply, the end are just some images for you to kind of experience what it is that we mean when we say that at a certain point or perspective, you're able to feel as though this object is completely solid, but from a different perspective, it feels translucent and porous. So this is exactly emphasizing the point about the different perspectives of how this wall performs. Thank you very much.
Would you like to show a bit your prototype as well that you have here just behind the jury? So time is flying and we have only 10 minutes for comments. Who wants to start?
Thank you for your presentation. Few comments, very interesting to go to a more aesthetic research compared to the previous group, which is more like about physics. And it's a domain that's a little bit not foreign for me, but more than physics, because I have less of an architecture hat here, but more of an engineer hat. I didn't understand what is global inertia. What kind of inertia are you talking about? I don't think it's very clear. Is it mass inertia? Is that thermal mass inertia? I guess not. Or is there some kind of new concept that I don't know about? So, sorry? All right. But yeah, I think that would be great to clarify what is this concept of global inertia. And I was wondering if you had thought about doing any comparison with light simulators. For example, you know, in architecture, you do 3D renderings, and there is today unbiased light simulators such as Maxwell Render or other software. And again, as a research project, I think it would be great to compare the result of the light patterns that those walls are generating compared to the simulation tools that there is today, to validate not your design, but to validate the tools of light simulating for architects. Then I was also wondering if you thought about using this idea not for light that goes through, but light that bounces on. For example, let's say you have a window that directly makes the sun go to a surface, and off of that surface to have different ways of scattering light based on the aspect of the surface, because it looks like it's only for controlling how light goes through here, not how it bounces off. And I see a direct application also of intimacy with this. So it looks like you've tried left, right to change the the direct light or diffuse light, but have you considered doing that up and down so that, for example, only the sky is visible, or at least when you're outside, you only see in the room from an up point of view, whereas when you're in the street, you don't want to see in the house, you know. Have you tried that also in this direction? Those are my comments / questions.
Maybe to start off, some of these concepts, again, similar to the previous research topic, will be better demonstrated in the design project, where we actually show the application of how this wall can perform in different circumstances, whether it's mediating privacy, whether it's allowing in air for ventilation, or whether it's creating different conditions of light. So this will be better demonstrated in the application part of the presentation.
So yes, to answer your first comment about simulating in a digital environment, we also did look at simulation in the digital environment and found that we needed to have a qualitative, masks and glasses. So we also needed to have a qualitative aspect, and this was difficult to assess in terms of digital analysis. You would get more sort of quantitative data, but you couldn't really tell, does this light look nicer than when it's bouncing off through this object? I think the second stage would definitely be trying to explore this in the vertical direction for sure. And this was now where the printability was something that chewed up a lot of our time, because I said to introduce an opening into a tensile, into a compressive material in itself is quite a challenge. So I think this is something that we aspired to, but we did not get to however we wanted to, quite honestly. I think those were the two comments I remember.
Thank you very much for the presentation and congratulations for your work. I see that you really well understood all the discussions that we had on structural performance, and I think it's interesting the way you applied the process in what we call this performance-driven design. So understanding the performance of an object from the structural perspective of the performance depending on the scale. I really like the different examples that you had in the micro, small, larger scale, and probably I would like to see a bit of a combination of both. Not only from the structural point of view, that I understand the work that you've been doing to challenge your design and achieve this the largest cantilevers and the larger openings, etc. But probably it would be interesting to play when you start with the performance of this design in terms of lighting, to play a little bit not only with these different layers of the same object or the same geometry just being repeated, but also changing the scale, changing the geometry a little bit, and probably challenging a little bit more in terms of light performance. Okay. So I know this is not a question, so but I'd like to see your comment on probably further experiments or so on.
Yeah, I mean, it would be definitely one of the next steps to be doing, like involving more than one scale at the same time, and to mixing them into into a different geometry than this one. Yeah, challenge ahead.
Add the last comment.
Yeah, you did a good job, but it would be really nice if you could now follow with some of the ideas that have been just said. Because I'm afraid you were designing a lamp, but you have not tested it with the lights on. And when you design a lamp, it's an object, but mostly it's a light producer. And although you have tried to test, you have not really done it to a way that you can get all the potential of this element. Because sunlight is not one light ray. Sunlight are many parallel light rays. So it behaves spectacularly. You should have created the conditions to have kind of a dark room and just put this on the window. And you would have, but not the dark room you created with one spot of light, but true sunlight. Because you would have seen all the effects that Grégoire was mentioning, how the light is reacting inside, and the whole thing would have become a lamp with a diffuse light. And that could have been, way more useful to test your ideas. So that's the next thing I would try to do, yeah, because I'm really curious on seeing. I'm sure this would look great on the sun, but I'm curious to see. No, it's kind of a final test. I would like now to go outside and do this. Yeah, let's open the door and let's try it. Yeah, but yeah, thank you.
I think it's a nice comment, and I think it's definitely the room definitely today is very dark, no? And we want to understand better how it performs. I think it's a good point, and the one of the simulation software is also. I think it's very important. Knowing your work from close, what I understood that you did is to actually make a simplification of light, understanding it as vectors, understand light as kind of two positions, to be able to deal with the complexity. But I think it's for granted, no, that this project needs to continue, needs to go to next steps where the inputs become more complex in order to reach to that geometry. But I think what I wanted to say is I didn't comment on the project before, but I think that this one and the previous project have something in common that I think is quite beautiful, which is the fact that they were designed from the conditions that they need to achieve. No, in your case, before drawing anything, you had to draw the light, and drawing light is difficult. That's why you do it as vectors, as a simplification. And your colleagues drew the heat, they drew the path, and the same applies to them. They've understood heat as a path, while it can also be, of course, understood much more complex. But I think the two projects share that particularity, that first the performance was drawn, and then it was used in order to then get the geometry to emerge out of it, of course, with a lot of construction knowledge, material knowledge, etc. And I think that this is something that is, of course, not new, because I think when we design a door, we measure what needs to go through it, and so things are always somehow related. But this is something that in this field of 3D printing, because we can be so precise with exactly where we're going to deposit material, create structure, create cavity, we are able to get into tectonic languages that are, I think, unique, no? And I think are definitely new. So now we're looking at them on the scale of the wall, on the scale of the prototype, and as we said many times later, we will look at them on the scale of space. But I think both of your projects are very convincing, because they also bring a kind of new design methodology out, and objects, I think, that are really contemporary and couldn't have been done in the past. So I think this is really, really exciting. Yeah, no, go ahead, go for it. And then we're gonna move on.
Sorry, I know we're rushing, but I really wanted to add something on this discussion, especially because you know how I am obsessed with the idea that 3D printing needed to finding his aesthetics. No? That is something that has to be found, invented. And I find it interesting because I have this thing in my lab that I say, wow, this really looks like in some kind of intestines. Then I look at there and I say, wow, this really looks like some kind of, I don't know, ass, no? Kind of, no? No, but wait, follow. What I want to say is that our body is designed to respond to the performance, no? Especially, there is this very nice example of Neri Oxman that says that our skin is capable to continuously change the performance gradually. No? So you have different kind of skins from the feet or from the hand, from the face, with different kind of sensitiveness in order to respond to different performances. So I find it interesting that we are having a connection in terms of between our body and the aesthetic you are bringing today to the presentation, between our body and the 3D printer architecture, and in the focus that both of these two projects at least are cases on which the designing is following strictly the performance as it happens in our bodies. So I think that there is something interesting to explore. And then since I have the microphone, I think you have an opportunity to work with color. I mean, if you work with light, maybe in the following step of the research, working with colors, maybe working with two nozzles, with two different materials, with two different colors. So, yeah.
There are very good comments that we'd like to continue the discussion, but thank you very much for the presentation and just wonderful comments. We have to move on. Please. Up.
Hello, I'm Brenda, this is Nita, and our research is about 3D printing vaults and domes without any formwork, using clay as a material. Our methodology is studying how these structures were built with masonry and trying to translate that into 3D printing while trying to understand the limitations of and the potentials of that comes with the change of behavior of the material during the drying process. So we study a historical timeline of vaults and domes dating back to 3000 BC. At first, they were very simple structures composed of simple brick layers, and they become freer when new structural strategies start being implemented. And we, for the first part of the research, were inspired by the Florence Dome, being the first and largest dome to be built without formwork in history. And we start exploring half-segmented domes. We create a catalog of those structures. And the reason why we do half domes is because if those domes are standing, that means the whole dome would also stand, and that could also be brought into the vault section of the research. So we create kinks along the force lines, and we create a wide variety of geometry to understand how that would behave. And we analyze the local inertia in these shapes. So we printed 15 out of the 28 geometries. And we observed that some of them fully print, but don't really keep their shapes. And some of them just collapse midway. So just to visualize it better, we can see the three best prints that we have. They have very localized local inertia along the force lines. Even though they're not as bulky as the collapsed ones, that force line is really what keeps the shape of the dome. And then as opposed to the unsuccessful prints that have more material and more global inertia, they don't have those localized lines, and then they start bulking in the middle of the printing process and just collapse. So for the next step, we started exploring vaults, and we wanted to bring the same principles from the vaults into that. We started very simple barrel vaults, and we create this catalog with 4 variables: the thickness of the arches, the base curve type, support, so walls and also outer kinks, and the distance or the span, the distance between arches. And we're using the same logic of kinks, but here they're kind of forming an arch that holds that supports the vault. The first test we did was with the thickness of the arches. So we analyzed the variation in the center of gravity of those geometries, and we could observe that the moment of failure for these two were always the moment that the center of gravity variation exits the support area. So that becomes kind of how we observe the geometries to know if they're printable or not. And then we start looking at different heights of curves. And we can see that here we have a lot of variation in inclination, but the center of gravity doesn't really vary that much. Then we start looking at semicircular vaults, and here we have a different challenge because the center of gravity is very stable, but we start having what we call a bridge between the legs of the arches. As the circle is scaled up, that distance becomes too big to bridge. And we compare it to the catenary curve, which is more printable and more stable in that point, the top point. In the last test is with the spans. So you can see as much as you space the arches, you start having a lot of buckling. That's not very exact because it only works for this scale, but it was good for us to just observe how it works. And then we wanted to have some parameters that could be applied to different geometries. First for the layer scale. So based on the thickness of the layer, we're analyzing the maximum cantilever that we can have, and also the bridge length that is printable. And then for the overall geometry, we base every dimension in the vault according to the span of the arch. So the thickness of the arch, the distance between arches, the height, and we try to relate all of those dimensions. And then we analyze the width versus height ratio of all of the curves that we worked with. And what we can see is that when that ratio increases, the bridge decreases. So the catenary shapes and the pointed arches have smaller bridges. And then we start inserting a third time of structure in order to be able to close the tops of the domes, the vaults, which we couldn't do before. So basically, we're just taking our simple barrel vaults and adding what we call ribs in order to be able to print on the critical area on the top. And what you can see is that once we add those structures, we're triangulating the critical areas, the contours on the top of the vault. And then it becomes printable because the span is much shorter. So here you can see how those ribs connect at the top, and they create kind of like a base where you can print on top of and close it. So we also just wanted to have some parameters for that. So basically in plan, we just have a maximum angle between the ribs, and in section, maximum angle between the top of the arch and the top of the vault. So basically just the inclination that can be printed. And to sum up, we conclude that the domes have a more simple execution. They're more stable during printing, but they're also more limited when it comes to the geometries that can be achieved. And the vaults are quite the opposite. They're trickier, they're more unstable during the printing process before they're completed, but you can incorporate openings and have more flexibility with the geometries. So for our prototype, we start looking at how we can deform those arches in X, Y, and Z, and associate them in different ways to create different shapes from the very standard vaults that we had before. We create this catalog just to explore the possibilities before we really start designing. So associating vaults and domes, different heights of arches, really deforming it in crazy ways. And our prototype is a combination of 5 arches of different heights. They're closed kind of with 3 domes. And our goal was really creating different spatialities inside of it, while minimizing the support area and maximizing the covered area. So we have 5 points where the supports branch out from, as you can see. And as it goes up, they start meeting, and then the ribs start growing, and that the top is printed on top of that. We had a lot of challenges moving to the bigger scale, because all of those parameters that we had and the analysis and everything, once you bring more weight into it and a thicker layer, there comes a lot of new problems. So we had to print in 3 parts, and we would print around 30 centimeters a day and wait for it to dry for 12 to 18 hours. So we printed for 3 days for a total of 12.5 hours. The tallest arch is 90 centimeters tall, and the whole model is 355 kilos. Yeah, and now we have a video.
As Ana Ramos was saying, it's 30,000 of history in 3 minutes. Congrats. Who want to jump in? Maybe Areti that didn't have the chance to comment on the previous one. No pressure.
Yeah, I mean, I didn't have something specific in my mind apart from the fact that I was, well, thank you for your presentation. I really enjoyed, let's say, your intention is very much design oriented, right? And I think that this is something very, very obvious in the outcome. And I know that you're working a lot with structural complexity when it comes to figure out how you materialize certain, let's say, catenaries or certain arches or certain domes. And what is more interesting to me in your project is the fact that you have tried to create a kind of a system that could eventually allow you to start bringing together a lot of different either arches or domes in order to create expandable geometries. And I think this has huge potential when we're talking about architecture, no? Because this is indeed allowing a deep knowledge, but also the possibility of customizing different kinds of spatialities, perspectives, optimization. You have been talking about trying to create the maximum space with the minimum, you know, like support area. I think this is something very important. I think that there is a lot that we need to learn from the Catalan Vault, you know, and those are principles that maybe you can start thinking on implementing in your next step of applications, but also what kind of complex geometries you can create in space. But I think this is a very clear example of a huge architectural potential. And there is a lot of discussion now of, you know, like how you can manipulate the surfaces of what we have here in order to, you know, allow certain performances such as light or such as, I think, thermal property. That would be really, really nice to see how you can implement principles of what your colleagues have been working on, because that would create a base of completing this more architectural idea. Thank you.
Thank you very much. Well, first of all, I would really want you to congratulate, because I think you really achieved a very important step in 3D printing. I mean, I really liked the study you did through the whole history of vaults, and you try to reproduce this in kind of in a matter of weeks. But if you look at what's being done in 3D printing now around the world, you'll see that everyone is still in the early ages, still just doing walls in stone, or in this case 3D printing, but still not yet facing how to cover a huge space, because everyone is printing vertical walls and putting something else on top of it. And I think that the way you achieved of covering a whole space without any scaffolding and only using this very standardized process of using a primary structure and the secondary structure and these ribs, and allowing with this kind of small ribs to first achieve the tip of the vault and then covering the space. I think it's a really important step. So I really wanted you to congratulate for that. I kind of agree that the final project is kind of very much design oriented, but I really enjoyed the initial process where you showed all the analysis that allowed you to cover this space, and I think it's really an important step. Maybe I agree that of course that there are a lot of things that you can apply on top of it. For example, especially when you understand that the ribs are kind of one of the main elements on the structure, you can play with all the rest of the surfaces with thermal properties or lighting or whatever. But I think that when going into the design, it's really interesting that you are not only focusing on the space you are covering, which is, as I said, a very important step, but also on the other spaces you are creating. I think that it's really, really interesting when you look at that prototype to see all the spaces that you are creating between the vaults that can be also used for other purposes, as a kind of extra spaces that you are already creating only by focusing on the interior space. So probably focusing on the whole possibilities of the system, it makes it really interesting. So congratulations.
Ladies, I want to congratulate you a lot, because what you've done here with this is kind of the Santa Sofia of 3D printing. So, you know, in Santa Sofia in Istanbul is when the Byzantine Empire or the East Roman architecture reached this super highest top on combining different systems of domes and on learning on different sizes of domes and how to create combined structural efforts all around. So, and getting this multiplication of spaces inside with this amazing spatial quality. So I think you have somehow really really found a way to go deeper into this big problem that we have, that is how to create the full space. And it's amazing, this, I made this joke that you went throughout 3,000 years of history, because you made first the research on the history of the domes, but then you wanted to test it yourself, like Santo Tomas. You wanted to, put your hand in the wound and check what happened, and then you get this amazing collection of failed structures, which also happened throughout history, but they just, because they failed, we have not met them, but we have seen all the collection of essay error trials, which is great. So I think it's super exciting. You could start thinking on how to combine these. Of course, these interior spaces also have the value of the Dome of Florence, which also has a space in between the dome that we see from the inside and the rooftop outside, and that amazing space. So you could create lots of opportunities here. So you should start combining these to create bigger spaces. And of course you should scale this up, because I'm really curious. I would really love to come maybe next year or in a few years and to have this workshop under this building. That seems like possible. You made the future camp closer, I think. So yeah, great. So thank you, congratulations, and congratulations also for the very good work you have been doing. I think you were drawing carefully at the same time with rigor and with the ambition for beauty all together, and that has kept until the end. And I think that also helps when we work on the technical part already with the beauty ambition, and then we reach the final results with success. So on my side, I'm really happy that I saw this. So congratulations.
Okay, very, very quickly. First of all, congratulations. I am really amazed by your project. Your research is super clear. You presented very well. So I really have to say, well done. And this project reminds me of one of the things I really love about Earth, that is that you can really build everywhere with the material that you just have just there. In many cases, in contexts that are sometimes lacking of natural resources, as desert zones, for instance, where we are lacking wood, and we always end up using concrete, cement, or other not so sustainable material for covering the structure, for the roofing. Here we can really see an example of how you can use just one material, the one that you have just there, and have a complete architectural design. So this to me is really, really marks a point. I really wanted to mention that.
I promise next one I shut up. Next time I shut up. No, I wanted to add something to your comment. That the fact that actually is on a mural is also kind of inspiring the idea that of the subtraction, architecture out of subtraction. So imagine like that this floor is not the floor where we built from there, but is something where we've been extracting the earth. So we have the positive and the negative that are fed one from the other. So I think that the model is especially beautiful and referring to a lot of things in this sense.
That's it, and then we move on. Yes. Yeah, I think the project, it always reminds me of this coin, this term, which is coined by So Fujimoto. It's kind of a primitive future, no? What they're trying to achieve in this sense. Sorry, I just wanted to add something through the chat that I was looking at. There were some questions about how do these structures, let's say these kind of compression-only structures work under earthquake, or their feasibility in real life. And I would like to take this opportunity to also ask Lapo, who is our dome expert now. Not anymore. Or maybe Guillaume, if you could say what he thinks about this as well, or even the girls, if you could answer this.
No, I think it's, of course, we should test it. This will be interesting. But the good thing of having all these ribs, especially the edge arches that you added at the end, which makes the system a bit more stable, for sure it gives robustness to the whole system. So I'm pretty sure that this system would behave very good, very well in a seismic area.
Okay, very much thank you.
Just super quick comments. I know that. No worries. Great presentation. I love the historical line of vaults and the catalogs that you've made. And I would like to be informed, because maybe I'm not trained enough in this area, what is global inertia and local inertia. Don't understand what is the physical reality of that. I wanted to know if you also experimented with buttresses to escape the catenary and go to like more semicircular shapes, buttresses on the side, like churches and other structures like that. Have you thought about like 3D printing with plastic? Have you thought about creating not wood form, but some kind of support for those bridges, like clay support at the same time for those bridges to be done? And that would also maybe open the possibility of not printing in layers. I don't know if that has been tried already, like because somebody talked about the Catalan vault, and the key of the Catalan vault is to cross the bricks, right? To cross the layers. So if we were able to print in 3D right away with support and then print the other way, maybe that would really create some kind of a network of distributed forces that would enhance the thrust standing ability of the arches. And I wanted to bounce off your comment as well, which it's great to use material that's right there, earth, it's amazing, but how sensitive this printing is to, and maybe that has been covered in previous years, but how sensitive it is to clay content, to the earth that you have right there. Like, is it super difficult to get the right mix to be able to do those bridges, for example? Thank you for your presentation.
I think we can answer a couple of them.
Right.
Quickly.
Yeah, we had to skip some parts of the research because our time was limited, but we did, I even showed in the catalog, we did experiment with buttresses. We called it like an outer kink. We didn't see a lot of, it didn't really increase disability in 3D printing, or maybe we just didn't go further very far. I got lost in all of the questions. Oh yeah, we also experimented with angled printing. So we tried both with the Cartesian printer that prints just horizontally and with the robot, so printing like angling the extruder. And we got some interesting results, but we had to decide at one point which line we're gonna go forward with, because again, we didn't really have time to do both. But yeah, so I think there's a lot of, maybe next year, the new class can go in that direction. I think there's a lot to try. It's all valid questions, I think. What, did I forget something? Oh yeah, that makes a huge difference. And yeah, and I mean, it's a lot of stuff that we mix, and I mean, a little bit of water that you add too much, it falls apart. So it is a bit delicate. Yeah.
Thank you very much.
Thank you.
Thank you. Speaking about support, you were asking if we use some support to hold these vaults and go a step further. The next group is about support. So, surprise. Así, claro, tenía que ser así. Okay. Okay. You want to press it?
Hello. Yes, good afternoon. We are Bruno,
Zachary,
and Francesco. Yes. So we are experimenting with supports. Can temporary supports be integrated in the process of additive manufacturing with clay for the construction of vaults, arches, and domes? Can the printing strategy minimize the amount of required temporary supports? And can those supports be removable and reusable? So in contrast with the previous group, where when it comes to constructing domes and arches that are in a very inclined angle, there's a necessity of having some type of temporary support, which is basically a structure that is built to support the final structure until the final structure is able to support itself. And in historically, it's been built with wood, and this is what we try to continue. When it comes to the state of the art, combining 3D printing and supports, we have two promising and contrasting examples of using wood in the previous research in UTEF and the styrofoam in the Penn State University.
So the first step of the research was to understand the relation between the span of the supports and the amplitude of this geometry. So we understood it through a jig with a flexible angle inclination. We tested 45 degrees, 60 degrees, and 75 degrees, as you can see on the screen, with the results, the collapses and the success. These were the tests. And this geometry came from the previous OTF, so the research, and we did these tests to extract the data, and we plot them on the graph to understand also for the future tests. Whenever we have to start a test, we want to know which is the relation between the span and the amplitude.
So we looked at different ways in which supports could be constructed, from waffle structures to diamond-shaped skis and linear supports. But one that was most interesting for us was the embedding of supports into the clay structure. The main reason for this was data that was, or a result from WASP and their investigations, is that we can print 30 centimeters a day with clay in order to let it dry before we can print the next layer on top of it. So that was a benefit when it came to embedding those supports, because we would be able to print part of the wall, embed the supports, and then later print on top of the supports when we needed them. And that enables to place the supports off the ground and take advantage of the limitations that are created by printing with earth. So we conducted some tests trying to use and analyze the printing on solid surfaces or on different skis, and testing different inclinations. So initially we tested without supports to see that it failed, and then understanding whether we embed the supports and have them go all the way through, or whether we place them within the wall and not have them visible from the outside. But in both cases, it created some problems because we weren't able to remove them. So we found that from all the different types of supports, embedded supports performed quite well, except for the reusability aspect of this system, which we wanted to tackle. So in order to do so, we looked at different types of embedded supports that would minimize the amount of material we would need and present removable options. In this case, we have a nested T support and horizontal embedded supports, which we could be able to remove. And both cases proved promising, but they still had cracks because they were embedded in the clay. So we tried to come up with a system called the X notch, which would lay on the surface and not go all the way through or be cast in the clay. In this system, we would use a belt that would go around the pillar that would receive the support, and it would be then held in place on a wall. So this module that we looked at, in which we cast or lay the support within, could then be part of a greater system, such as a wall, to then print an arch on top of, or cantilever. So this is the printed result, where and then we then printed an arch on top of this, or half an arch, to see how it would perform. And the results were quite promising. Although once we printed and the clay dried, we still had the same issues where the cantilever started separating from it because we introduced another object in the clay. So that led us to this pivotal moment in our research where we notched these supports and not having them continuously throughout the surface. So we just let them rest in the clay, and that provided the possibility to raise the supports further. And
yes, and our research is about clay as much as it is about wood in a way. So we went through a process of trying different iterations of the supports and how the wood connects to the wood itself and how they support these cantilevers. And of course, how the supports are introduced inside of the clay. And as Zach said, we designed this way of putting the supports in a notch. And that means that we need to have this pieces horizontal plate that rests on top of the clay, and the vertical element that acts as a structure touching the wall. And that led us to develop a smaller detail of having this wedge as a mechanism that you could put inside. You could place a support and take it out very easily. So having these triangles cut at 5 degrees that we place first, and then we come with the horizontal piece and connect everything so it to be stuck together. And this would be the process of assembling these and using still the belt as well as this wedge support. And you can notice how we had to introduce a branching. So we have 2 points of contact in the wall or 3 skis. And that comes from the geometry that we had to define.
So as we saw throughout the whole presentation, the retraction is an issue, a huge issue for the 3D printing clay, especially when we insert another object, in this case, another material, in this case, the wood touching the clay. So we analyzed this phenomenon throughout the point cloud and a photogrammetry to foresee what could happen in a bigger scale. And we saw that actually the shrinkage after the first moment, the print, and after 2 days is quite significant. And in this tests, the vertical shrinkage was bigger than the horizontal one, but of course it depends on the geometry. And we can apply this analysis also to our final prototype to foresee in the next times how it's going to behave. For example, this prototype we will see later, how it behaved and the cracked after the printing. For the model 1 to 5 scale, we need to close, to have a closing strategy because of the amplitude of the cantilever. So once we reach the top level of the arch, we need to close it. And in this case, we decided to continue the cantilever shape at the same inclination up to the moment when both cantilevers touch each other. So this is the final result of the model of 1 to 5 scale, as you can see also on the table.
Yes, and all of these things are applied to when you come to the 1 to 3 scale, which is the prototype there, and everything has to be scaled a little bit, and we have to kind of re-understand all of these components, and these are the final iterations of supports that we came to, and we went with the right structure that seemed more stable and more well-defined.
When it comes to robotic strategies, before the production of the final prototype, during the tests, one of the robotic strategy was to incline the extruder gradually. So starting from 0 degrees up to the 15 degrees at the final point of the first cantilever, and keep printing at the same inclination degrees of the extruder for the second cantilever. Regarding the splicing, we have a gradual splicing throughout the whole prototype before the steepest cantilever, and also a strategy with the alternation layer to have a half splicing on the back wall and the double splicing on the cantilever.
And when printing cantilevers with side walls, we realized and knew from the beginning that straight lines are our enemy when 3D printing with Earth, because it invites cracks to happen in the surface. So we tested different kinks that would happen in the surface in order to reduce the amount of straight lines we would have. And this is the final geometry we came to, which also provided more support when printing these cantilevers on the side surfaces and minimize the amount of buckling. At the back, you can see the different tests that we ran and the buckling that happened in those iterations.
Yes, and the same cracking happens on top when these two pieces, these two arches, they connect, they create this bridge. So we introduced a keystone, as we call it, which is a piece that is not here, which has been removed in the center, which allows the structure to move a little bit. And we also introduced this metal element that allows to gradually adjust the structure. So we've been doing this for the previous days, coming back to it and slowly allowing it to touch again, because it tries to separate and we have to come back and touch during the drying process.
So you can see in this image the first moment after the drying process and the moment after the loosening supports.
So finally, our final prototype was 2.3 meters in length in printing, kilometers in printing length. Took 13.5 hours and was the result of just under 600 kilograms of material.
Yes, and when it comes to wood, at this scale, we had about 30 meters of wood and divided into 84 components and 4 bolts, if I'm not mistaken. And the conclusion will be the pivotal point is to remove the supports, which we haven't done because the structure is not completely dry, but the objective is.
Thank you.
I think you have a small priority in this one.
Okay. Thank you very much. Congratulations again. I think that you've done a great job, and I really like again the process of how you evolved from very simple experiments to adding complexity and especially the complexity of using 2 different materials. I particularly liked the way that you consider the timber structure supported directly on the clay and not on the floor, because it probably gives you the capability of adaptation of the timber itself during the construction process, which if not, you would have these differential deformations that would create for sure some cracks. I really don't understand why you changed this center timber piece by this kind of metal piece, or was it a different experiment, or do you just change this piece here?
Aspect here that you need to answer with a microphone. What is this metal piece?
We did have a wood connector there, but that meant that the structure was very rigid. And what the structure is trying to do is trying to break apart, and it creates a gap between them two. And what we try to do with this screw is to have a way to adjust this so that the structure, both structures could slowly collapse and the clay would touch again, if that makes any sense. So the structure separates, we come with this rod and we adjust so it slowly touches, and we do this again for the next 7 days. So yes, if that was clear.
Yeah, the key point here is obviously shrinkage and the self-deformation. I mean, if you see the construction process of any arch bridge, you'll see that there's a step at the very end of the construction of the arch where you really place a jack, a hydraulic jack on the top of the arch, basically to compensate shrinkage and I don't remember in English no, it's kind of fluency, but it has a specific name in English. But there's this long-term deformation of concrete that you need to compensate with a jack. So you basically literally place a hydraulic jack on the top of the arch, and you expand this jack to compensate this this deformation, and you end up just putting more concrete on top of it. So this effect is exactly the same that you experience here. So instead of replacing this timber place with a metal place, which is doing basically the same, you really need to kind of invent a kind of, even if it's a manual jack, just to put some kind of a triangular piece that you embed in the timber that is expanding little by little, and you end up printing this central part, because the effect will be there. I mean, it's not about changing the support. It's the deformation that this will experiment in, especially in a larger scale.
That has been a key aspect of the question we had in this project. No, so how do you compensate something that want to move, that is the earth, with make a dialogue with the wood? No, and so for a long time they try to find adjustable jigs here that can fit, that just support on it, that don't grab it, so that there's movement possible. All these structures is kind of movable, adjustable, can just adjust to the earth. And one of the trick here, not finished to be solved, was to predict this deformation and let so print a bit bigger, a bit larger, and let it collapse into position. No? The hope is that with 3D printing, being able to be so precise about geometries, and then they started to look into scanning to be able to predict and maybe learn from this deformation so that they could anticipate, say, print something already deformed and then let it go into position. So the wood structure would have to adapt to this deformation slowly, releasing, hopefully all made in wood, but that would be also another element. What do you think about these ideas that I try to summarize?
I mean, it's not new, actually. I mean, when we are doing a very large cantilever, we use this initial deformation to compensate the deformation. So even if it's still structure, so this, I mean, I'm not saying that there's nothing to invent, but there are a lot of construction techniques that are applicable also in 3D printing, especially when doing this kind of large span structures. That I think it would be interesting for you to investigate on that and see how to apply on the 3D printing. My last comment is that I really like that you don't use a full scaffolding. You just concentrated on a certain arches and certain lines and try to cover the space between them. I mean, like minimizing the external support and trying to maximize the use of 3D printing. So I think it was a quite interesting strategy. So congratulations.
Thank you for this presentation. Was really like the video editing, actually. It was very great, I think, at the end. Yes, to bounce on what has been just said, regarding this cracking at the top here, I think that there is few factors that are favoring the fact that it cracks there that could be, that you could get rid of. Of course, it's a weak point, but I was wondering if you had the same thickness all the way. For example, if you printed more layers on top, maybe it would have contributed to not crack there. Also, anywhere there is a discontinuity, that it's going to be prone to crack, right? And a big continuity that I see here that leads to a more general question of choice of material for scaffolding is wood and earth that don't behave the same way. So wood was probably very dry, so it doesn't expand or contract that much unless you have humidity change in your room. And earth is very wet and it's going to only retract, right? So it's two behaviors that are completely different that will not work together well. So hence my question, why wood for doing the support? Is there something else that we can use? Could it be, and it makes the link with the previous presentation, could you think about doing support that you remove afterwards that's made of the same material so that there is like an isotropic behavior in terms of retractation? And to link with the first video that we've seen, just an idea here, but to get rid of it, why not burning it? You know, like it's in the structure and you create a channel so that when you put heat, you just get rid of the scaffolding by burning it, which would have the benefit also of maybe being able to build faster because you would sort of fire the structure as you print. Just an idea. That's all.
I said just a bit tricky because it's whenever you need to file, we saw it with the first group. We need to consider so many factors from the clay, if it's wet, if it's dry, they behave in different ways. Whenever it burns, if we get burned too much one side, then the other side is going to behave in different way. I mean, it's an idea that it came out also throughout the 6 months of the research, not specifically with our project, but in general in the whole program, but especially when we were doing Phoenix. But it's very tricky, and with this amount of time, it's very. I mean, it's.
Also, if you burn it, you cannot use it again, I guess.
Wood is readily available to many communities and countries in the world, and using simple cuts to make those supports, we thought it would be easy for almost anybody to create those supports and replicate the system while they're printing their building. So it was more, and it's a sustainable material, more sustainable than using styrofoam, as you saw in our state of the art. So that's the main reason why we chose wood. Mm-hmm. No, of course, but in many. Yeah.
I want to add something that goes along the line, but that Zach mentioned in the presentation, which is that when you say straight lines are our enemies, no, in this. So the question of contraction, I think, not just with clay, with other materials, is always really, really, really difficult in construction. And I like the fact that we have now two projects in front of each other, the one of these curved walls and the one of this support system that's actually, from its volumetric definition, is already looking for the straight line, right? The difference between a curve and a straight line is a straight line, when it retracts, it cracks, while a curve, when it retracts, it deforms. And that is something that throughout the program we've been discovering over the years. It's something that is really fascinating, but also highly contradicting, because I mean, often in architecture we are looking for planar surfaces. Our walls are planar. Of course, we also dream of an architecture that is curved, but so far we all live in houses that has also, because of density, because of so many criteria, the necessity to be straight. And I think in this project there is this question of, or there is this necessity to work with curves. There's this necessity if we want to make a straight wall, and that's why I think that the previous two are also very successful. In order to make a straight wall, you need to integrate the curve. If you go for a straight line, it's just going to crack everywhere. The material itself is not going to be able to deal with the retraction. And I think there is this beautiful ambiguity, you know, about, in order to look for these lengthy structures as the one that you have, it's a matter of finding inside this way to let the material move locally while leaving the general geometry stable. No? And we've talked a lot about this. You've mentioned in the presentation, you've made, I think, a huge effort by designing the infills, which it's a shame we don't see, but I encourage you to look actually from the inside. And you've managed to put as many curves as you could in there, and I think it helped a lot, the retraction and the drawing of the piece. But there are still some, and these are the ones that are giving you trouble. No? So I think this is a really beautiful question for the future. It's about how to make a straight line with curves. No, and it's as contradicting as beautiful, I find. But I liked a lot the way that you explored that, because I think it's very meaningful, and I think you're definitely adding something to work that has already been done the years before, but you've really managed to push dramatically further. So I think it's really good what you've put on the table.
That's an interesting comment, Eduard. Thanks for that. You're bringing a lot of different thinkings, no? I think that, you know, like first of all, I really appreciate the fact that you're taking a very, very difficult challenge to solve, right? It is a difficult challenge to try to combine two different materials, radically different materials in terms of performance, in terms of properties, and try to mix them together, not only to create a base, but also to somehow create almost a multi-material piece, because at certain moments, this piece needs to perform in a way that it defines its final state, no? So both properties of the material should come together. I was continuously thinking that, and that I was also thinking about this last year when wood has been used in a couple of prototypes. How can you create a support base of wood which allows the flexibility that you need for the earth to dry, shrink, and take its final position, no? And I know that you have been working with these details on the joints, but you know, wood, like it's also very, very easy to manipulate or to mechanize wood so that you can have it in a much more flexible, no? Just by engraving it in different directions, you can start having also based on the density of that engraving, you can start having different kind of flexible or less flexible parts, no? And I think that this is maybe what I miss in this project. Understand in a deeper way how your earth piece will work while drying, you know, how it will perform while drying, what the geometry, of course, that you are choosing, how the geometry will affect the base, and then try to be much more sophisticated in the design of the wood base as well, no, rather than the earth. Because I think there it would give you like this kind of counterbalance of that secondary material, which I know that it is a formwork and I know that you will remove it and everything, but I think it deserves a much more, let's say, depth on its design so that it can work hand to hand with your earth piece. And I just to also comment a bit on what Eduardo was saying, I think that I'm not sure if the challenge is to do straight lines, but I think that you also need to somehow define or manifest what kind of geometries it's possible to do with that kind of system, no? And then, you know, maybe in certain directions you have a straight line, but then, you know, maybe if that is a bridge, or I don't know what could that be, it has a certain inclination along its length, no? But then according to the length, that kind of inclination might also be totally lost. So it's not about a straight line. It's much more about, you know, putting curves together and creating a surface of a non-linear elements. Yeah, but thank you for the effort. It's great. Isabella?
Thank you very much for this very nice comment.
shape to continue straight for another hour? Hasta 7:30. Por esto. Nos queda 4 proyectos de arquitectura ahora. ¿Sí? ¿O quieren un bio break? ¿Atacamos directo?
Okay. Yeah. Huh? We're going to do a 5 minutes break because we have 4 projects now to look into. So, but it's going to be literally 5 minutes. So we start again shortly. Thank you. Really tall. Oh, no, you guys are finishing. No, you guys are starting. You guys are starting. You can come on the stage. We're gonna start. It would be great to have more time, but unfortunately we don't have that much. So we're going to get back to the presentation mode. Yeah. If I can ask the guests to come back to the front. Wait, I'm gonna feel. All right, I'm going to ask everyone to take back their seats. Hello. Hello, hello. Okay, so we're going to open now the second part of the presentations, in which we're going to look at applications of all of this incredible development we've been seeing until now. So we've got 4 projects coming, and we're going to spend 10 minutes per project for the student presenting, and to have then 10 minutes feedback. Right, so let me pass the microphone to you guys. No, well, maybe just as a quick note, the studio projects were developed with the students writing their own briefs. So from the teaching staff, what we have actually selected is different conditions, different sites, different contexts under the form of climates. So we have 4 projects that are all located in very different climates. From then, the students crafted their own brief, decided for who they were going to build. One common theme is housing. All of us, all of the projects are looking at the question of domestic architecture. Yeah, but I think that is where we left things for you guys to take on. So, are you ready? Wait.
So, good evening, everybody. Myself, Roshin, TK, and Timur. And we are working on the project 87A. And we are working with a continuation of our research of how we can heat a residence with minimal heating demand. So as an intro, heating demand in the world, more than 50% of residential sectors are consuming energy in very unsustainable manner. So how the advancement in 3D printing can be used for minimizing this heating demand? So what is the difference between a 3D printed wall from a conventional wall? So the first point is we can incorporate the cavities inside the wall. And the second one, we can minimize the consumption of material. And the third one, we can create any kind of complex geometries with minimal support. So what is the difference between a conventional heat distribution system from 3D printed system? So by understanding the features of 3D printing and advantage, we are proposing a residential project by making the elements of the building, such as the wall and the floor, as a heating element. So the site is in Kazakhstan, having extreme temperature of -35°, and with an average of -29° for 7 to 8 years of 8 months. So as a fact of this extreme cold, we try to understand what are the problems. The first one is the difference in temperature between the internal and external surface. So, and the second one is how to contain the heat generated inside the space. So we have the solution is the first one is decreasing the surface area by maintaining the volume of the occupancy. For example, the igloo. And talking about the second strategy, it is using earth as a shelter. So it minimizes the surface of exposure. So we are embedding our building inside the earth, so it can have an insulation from the exterior. And the third one is using ventilation shaft, as in Canadian tube. So this is used to ventilate the wall by using a constant temperature through this shaft, so it can circulate the air inside the wall itself. And the last one is the building orientation. So in order to harness the maximum energy, we have oriented our building such that during the summer season, we can get more energy. So we try to combine all these strategies such that the first one is making compaction, so reducing the footprint and making it very compacted thing. And the third one is making it embedded in the earth and rearranging such that it can harness the maximum energy. And the last one is the integration of the ventilation shaft.
The place we choose is rich of timber because of nearby forest. Also, it's rich of the clay and sand. The soil is rich of it. Kazakh people before were nomads, and they used to have lightweight mobile construction units, which is called yurt, which is covered with animal skin. And on the right, you can see vegetation, typical terrain. Here you can see a site plan of a construction field, which is the size of 20 by 30 meters. And here comes the road to the field. At the bottom, you can see Riur Irtysh, and by contour lines, you can estimate the slope of the terrain, which we choose. Problem of urbanization in Kazakhstan can be solved by using suburban areas for living. And since winter in Kazakhstan is quite cold, it can be implemented a sustainable way to heat the houses. Here is a soil profile of the terrain we choose, and we don't need the first layer of organic. We need a clay sand layer. After which you reach the gravel.
So as he said by Timur, we have a water body on the southern side that create a local wind from the south and a prevailing wind from the north. So as we are working on a performative design, we have to consider all these facts as well as the orientation of the sun. So since we have 6 meters of the condor and having a plot area of 30 meter by 20 meter, since we are using our strategy, we try to level our residence in 3 floors. And as a reference for our construction, we are using the Technalia project by IAC and Technalia for a cable robot that can use a bounding box of 15 meter by 11 meter. And here we were upgraded our version such that we can use larger span and we can consider our elevation of the site. So we can print up to 20 meter by 13 meter by 12 meter in total bounding box. Okay, so unlike the conventional system of spatial integration, here we try to map the heat requirement and how long we need to heat the space and what are the number of users and also the diurnal heat demand. So based on this, for example, we try to understand for a bedroom, we need to heat the space more and it need more heat capacity, more heat. So these are the main things that we understand while designing the space. And we try to arrange everything into our site such that we try to incorporate our strategy of making most usable spaces with the earth, in touch with the earth. Now, the next thing is how we can map the heat source. So we try to map our heat source such that it can heat the space very uniformly through all around the space.
So as we previously discussed, we are back to our wall. And so the idea of generating a design out of a performance line, still we have the idea of that. So keeping that experiment, we are going to apply how to make it an architecture. So we start by locating our walls. So how a wall could be located. The first one is based on position, which means, for example, I could have an insulation cavity mass layers of different walls, or I could have a mass cavity mass, depend upon the orientation of my wall. And the second one is, of course, the surface area. So the more surface area I have, the more the heating demand I am going to radiate. So here you can see that the surface area really affects where I want to place my walls and how I'm going to interconnect. So here you can see we try to study about different kinds of walls, how we can bifurcate or how we can integrate it with normal things. So generating meaning. So this was the conventional way. Now that we have a single line that is a heat, then that means I can think of a bell in a given space. I can think of a fireplace in a given space, depending upon my area of heat demand, or depend upon where I want to position my heating points. And also the 3D printing architecture really allows me to print these complicating things with a simple idea or these complex ideologies. Of, for example, you can see along the different spatial lines, the wall can perform in different surface area and integrate. So you can have an amazing textured wall, but it's really something that is going to talk about the heat in the space. So you can see the wall, the section, and you can see, you can read the heat lines, the point of the heat. So after saying this, yeah, so this is how we generate our components. So for example, after we functionalize our buildings, this is a new idea of designing our proposal based on the idea that we have is heat lines that we need to connect the walls, the roofs, the components of the building. So here, for example, I have a fireplace there. I have a floor that is going to be heated. I can take the heat throughout my building, depending upon my my demand. So then integrating it with a structure will come next. So here, for example, we try different kinds of structures. So depend upon the terrain that we have, we ordered our plates. Then my primary structure will be a load-bearing clay wall. And my secondary structures are, because of the semi-availability of materials, timber, I have the timber. So this will be overlaid with the heat. So this is our new way of thinking the plan of our residence. So here you can see that I have a family area, I have a study area. The most congested area that you see, the dark part, is the area which is load bearing, that channels the wall. So it's really performative in a way that it tells you what the wall is about. So here is an impression that we have to explain what the inside of our house will look like. You can see the fireplace. So coming to the printing.
Yeah, as for printing, it consists several stages. First is transportation of all the equipment we have to the place. Then it's about a compaction of soil for foundation of a frame of the printer. Then it's erection of frames and assembling of the printer on the site. Next step, excavation from the site, where we excavate our sand and clay. Then we prepare printing material, and then it's transportation of wood for structural elements, timber. And the last one, it's the printing itself.
The team which can make a printing consists of 5 people approximately, and time for printing, it can take around 2 weeks per floor. The building has 3 floors, and approximately it can take 2 weeks to print 1 floor, and maybe a month and a half to finish all the printing for the house.
We can conclude that with the question, how the future can we predict a future that we can integrate 3D printing architecture by replacing the conventional heating and cooling techniques of our building. So this is the question to you guys. Thank you.
Thank you. Very impressed by the work you've done, honestly. Congratulations. So here's my chance to say my other comments about this. Obviously, it's great to be able to distribute the heat throughout the whole building, but looking back with the system, the technology that you came up with, I think it would be great to actually integrate some key elements in making wood burning very green, very efficient. And I don't think you tried with wood yet, but there's the notion of secondary air intake, which makes the combustion total, which is key to have no emissions. So I think this is a big help, to think about integrating secondary heated air to arrive in the combustion channel, to burn all of the other gases that are left to burn. I think that would be a great implementation of this, and quite easy actually. Also, with what I know from those kind of rocket mass heaters is that the sustainable aspect of the combustion is based on the fact that it's very high temperature. So I don't remember exactly what temperature you were burning here, but we're talking about 1,200 degrees Celsius to make sure that every gas is burnt. I know we build with refractory components that are not able to crack. I don't know if you tried, it would be a good idea to try to print earth with additives that are refractory, because at 1,200 degrees, it will crack. This is going to be those problems times 1,000. and yeah, that's basically it. Again, impressed with your presentation and your envisioning. And I would just argue on the fact that I wouldn't heat up the master bedroom more than the dining room. I think the living room where you work on the computer with your frozen hand on the mouse is the place you want to heat up more. Thank you.
Still doing walls. No, I know you didn't have time to change the project, but it's for further steps. Yeah, at least I like that you try to take the behavior from the wall and distribute along the whole building, which is a first step in going from the wall to a more complex system, which is I think it's an interesting step. And maybe what I liked also an exploration of you didn't mention that much when you were talking about insulating one face of the wall and using this insulation just to transmit the heat to one side of the wall. Probably there's a second step to investigate is to print with both systems. I mean, printing the clay, which is going to be the structural element that is 3D printed, but you can also spray sand inside the same wall with another nozzle or whatever. And maybe I disagree that it could crack in terms of when you do when you work with copper or some other melted metals, you can use sand as a mold for that. So if you, instead of a refractory element, you use the sun itself that you are using inside the wall for insulating. Maybe creating this bed as a sun bed could be, I don't know if enough, but probably there's an opportunity to use, without changing the system, to create this chamber that can really achieve this really high temperatures. So it's another interesting, yeah, we can discuss that. Oh, congratulations.
Well, congratulations for your work. It's very interesting. Maybe one way to enhance the fact that we are still building straight walls, as Gia said, is that you can definitely integrate some passive heating system here inside, because you have a structure that is already made and conceived to store heat, to store active heating in this case, and you have straight walls and you're already putting glass in your building. So you can just think of a different way of organizing the glazed parts so that you can catch some solar energy as well with the very same device that you have there.
And in a way, I think you can extend that comment also to temperatures, no? Because you guys are talking about heat a lot, because this is what you focused in your research. But I think a lot of these strategies, they can also apply to cold, potentially. And then I think then the question of gradient comes in, right? Because maybe some of these spaces, as you say, need a certain temperature for a very long amount of time, but for a very short amount of time, and other spaces might need some much more shallow temperature. So that can connect to the length inside the wall through which a heat needs to transit. So I think that then the kind of way to design the building, it becomes, of course, very complex. And I think you guys managed to go through a very difficult process, I think, of design first through these heat flows, and then afterwards defining what are the kind of structural elements, spatial elements, what defines the space that actually can accommodate these fluxes of heat. But I think, of course, it can continue to be developed into a system that is even more complex, which is also managing the coldness, but eventually really understanding the house as a system of cavities, of tubes, where you can also incorporate the Canadian well, so getting some air from the outside that goes through the ground in order to already heat up. I mean, it's a huge game, you know? And I like to think that this technology will enable people more and more to design according to a very precise performance, or a very complex performance that they might want to have into their building. And I think you've done it with a lot of success, actually.
Maybe we can really push this concept further. Here you have your heating system, when you have the air that is going from very hot to warm, and then to cold, and then it's exposed. And you also were classifying the different spaces of the house according to which one you want to heat more and less. Maybe you can think of the whole spaces, of the architectural spaces, as the cavities that you want the air to pass through, and to have the heating system starting from where you really want to have more heat. And I totally agree, that's where you work with the computer. And then little by little it goes to the bedroom, and then at the end to the toilet, and then it is exposed. Maybe you can really apply it as an architectural principle and not just as a heating system.
To bounce on those two comments, I think something to imagine is to take into consideration all of those physical phenomena that you talked about before: the sun, the wind, where we want to have warmth, when, to have that as inputs in a I don't know, like, I'm not an expert, but in a grasshopper definition or something like that, and you give the shape of the building. And it automatically creates the cavities that it needs, where insulation is needed, where thermal mass is needed for capturing the sun based on light. So imagine a definition where you have light angles, wind angles, temperature targeted in rooms, and boom, the cavities, the walls are automatically created to optimize that. Insulation somewhere, heat mass, I mean, you get the idea. I think that that would be kind of like a very interesting goal.
Just a small comment also from my side. I mean, I think that a lot of things have been already said, but to me, especially when we're talking about, when we are talking about walls that they are able to somehow perform as kind of heating elements, passive heating elements, there is a need, I think, to explore it in more detail in section, no? Now I know that you are, I really like, you know, like to start see the plan of a house with this kind of cavities that they start to infill the walls that traditionally we have been hatching according to whereas these walls were load bearing or not. And now there is of course a different kind of hatching that is related with certain performance. But I would also like to see that in section, because I think that especially when we're talking about heating and about how we can optimize heating, then there is an issue of, you know, what is the height of my building? Where do I really need to heat? You know, like there is a certain height in which I need more, how warmer is being moved inside the space in itself, as Elisabetta very, very geniusly said. And I think that this is really something that requires a kind of a more slicing down or sectioning in this work. Otherwise, yeah, I think it's a very interesting approach. And it's a very possible, let's say, application also, in the sense that, you know, when you see an image like that, one of the main problems of earth architecture is that actually people believe that this is like for poor people or for, you know, like developing countries or something. And then when you start combining it with materials or with, let's say, type of spaces that they are more familiar with people, it's also maybe a way to get closer to some of these applications, no? And then of course, making the other step of being much more radical into what this material wanna be, rather than what do we force it to be. Yeah.
Just to add on that is, I'm really in favor of earth, of course, but all of this would still work with concrete, you know, like thermal mass, the cavities with for insulation. So if people are really like not willing to have earth, if there's still people like that, and they want to have concrete, what you're proposing here would still work.
That means there's still work to do, no? Great, thank you guys. We're gonna jump to a different climate, very different climate now.
Our project is named Banyan House. Banyan trees are known for having multiple roots that branch out and meet in the middle in the primary trunk. This allows the tree to grow horizontally and gives it more stability. And we're inspired by this in our project and in our structural design. We are designing for a tropical climate, residential unit for 2 people who want to live connected with nature. And the architecture in these climates are characteristically very light and open and airy. And so we ask ourselves how can we translate that into printing with clay and have a very open and ventilated building, which isn't what we usually see. Because clay architecture brings some constraints that usually result in very compact buildings with thick walls and small openings. And we think 3D printing has the potential to change that and break those constraints and have buildings as flexible and light as what we see here in the turtle room, built with bamboo. We also want to take advantage of the locally sourced materials in Thailand. So bamboo that is largely available there, and also timber, and associate that with clay. And also take advantage of the local construction techniques and avoid the need for very specialized workers. So, so our climatic challenges are related to high temperatures, high humidity, and a lot of rainfall throughout the year. And to tackle that, we have some climatic strategies in the design. First, minimizing the contact with the soil, lifting the building up to avoid the humidity, maximizing the surface area to minimize the heat gain, multiple ventilation strategies, so stack ventilation, cross ventilation, having a lot of shading above the openings, and studying the orientations of the building to understand the needs for each facade. Our site is located on a slope by the water and also connected to the woods. The topography in the site brings some ventilation dynamics due to the slope and also for being close to the water. And we want to take advantage of that in the design. We studied the climate, first the wind flow, which speeds up towards the top of the hill. During the day, the cold air comes from the water, and at night, that dynamic reverses. So that's also taken advantage of in the design. We also studied the humidity, which also reduces towards the top of the slope as you move away from the water, but it's still high in contact with the soil. And then we look at the sun path and the levels to first understand how we can build in this site. So we feed this data into our first program distribution studies. We do some more sloped studies and other more vertical, but always keeping the humid areas towards the top or the exit of the air in the building in order to avoid bringing the humidity from those rooms into the common spaces. And we define an ideal distribution of the program around the central staircase that would act as a ventilation shaft. And then all of the rooms are distributed around it in kind of a stacked manner. The ideal robotic system for our needs would have to be very stable and also adaptable to the topography. So we choose the WASP Big Delta. It can be built without any need for scaffolding, so it's easier to transport into the site. And we are proposing a little change in the dimensions with a diameter of 10 meters. And then we would also have to have longer legs to adapt to the topography, of course. And then we start doing some structural grid studies based on that. Radial grid, an angle grid, and an orthogonal grid with various types of distributions and densities. And we choose the regular radial grid as the best solution for our strategy of having a central staircase. And our structural system, like we saw in the research, is defined by an association of various arches of different shapes and heights. We study how to connect them and in various support points and associate them, verticalize. And these 3D studies kind of define our structural design. So our building is first defined by arch rails that shape the vaults and the arches. Then the primary structure that is clay printed, followed by the angled bamboo arches and woven bamboo surfaces that shape the facade and create shading and ventilation. The timber beams to support the floors and the staircase. And we study the orientation of the building in order to make sure that the cold air is always coming through that shading facade, going through the floors and the central staircase and out through the top openings. We elevate the building using the arches, and then the first floor is just an access platform. We are designing for 2 people. So in the first floor, we have a bedroom and bathroom combined, and the only wall in the whole building for privacy in the bathroom, followed by a work and recreation area, a living room, a dining room, and lastly, the kitchen and laundry on the top floor. And our goal was to minimize the clay surfaces in the interior and keep the ventilation uninterrupted in all floors and also the views, and having views to the water and nature in every single room. And in the clay surfaces that we do have, we wanted to maximize the surface area and create air pockets within the walls for insulation, and also to minimize the heat gain with the radiators. Yeah, and we studied the orientation, like I said before, so we want to ensure both cross ventilation and stack ventilation. And according to the orientation, we have different needs. So in the south facade, for example, we need longer overhangs and balconies to protect from the solar radiation. And in the north, we can have more open walls and woven bamboo for permanent ventilation. We distribute the units on the site, keeping in mind that the ventilation should be uninterrupted, and creating these platforms in between them that connect the street to the water, and also they end up being like a common area in between the units. So our production starts with building the structure for the robot and the decks for material storage, followed by storing the material, which doesn't have to necessarily be done in one day, but we put it in the second step. We would need 89,000 kilos of clay to print the whole thing. Then start mixing, which would also keep happening throughout the printing. And we estimate around 445 batches because the printer holds 200 kilos per load. And then we would start printing first with concrete to elevate the floor, and then printing with clay on top of that. And we're estimating a total of 12 days for the printing. We would maybe be able to print 150 centimeters a day, and then wait for that to dry, and then keep printing on top of it. And then we would need another week or so for all of that to print, or to dry, before we can build the bamboo facade and add the timber floors, taking about another 5 days. So our system is capable of adapting and multiplying and aggregating. So even though we designed for 2 people, it could possibly become a shared living unit, or we could have different dynamics with the circulation and the staircases, possibly using multiple printers at the same time. And then to open the discussion, we just raised some questions. So how can the system be customized and adapted to the local materials available? What are the logistics of 3D printing buildings in difficult topographies and in remote locations? How can clay buildings be made lighter and be less solid? Can we think of 3D printing buildings in a way that is freer and more ventilated, ideal for tropical climates? Thank you.
Cool.
I'm actually still processing it. That's why I didn't jump on the microphone, because there is something that I find very seductive about this proposal. I like the openness. I like how you how you make us believe that this can be totally a Balinese. Oh, sorry, what did you say? This Bali? No, in Bali. Thailand. So we believe this thing that probably in Thailand never saw in their life, surely. We believe that can be something that, you know, embed with the local tradition. So that's very special, because manage that you, with a totally different technology, you manage to get the feel of this local construction. So that's not easy. I like the way how you combine with the bamboo, the earth. So there is a lot of sensitiveness, and I also like the fact that since you have a vertical construction, you develop the house adapted to that in a very smart way. You eliminate the walls because you just put the different rooms in different floors. So you manage to reinvent the housing based on your technology, which is something not so trivial. On the other hand, I have some doubts about how you actually gonna build it, but I know, okay, that's fine. We try to make a guess. But I also have a doubt. I don't end up understanding how the arch is supposed to close at the top, because you demonstrated that this works because the dome closes, but then you showed in the render the dome is like broken, like it's open up. So are we sure it's gonna work? Ah. Okay. The arch is entire, but the half dome are yeah, I think it's very interesting. Something Gothic in Thailand, out of earth and bamboo. It's like, okay, you're opening a new chapter, but it's not bad because somehow stays together, somehow makes sense, even if the references are so diverse. So I find it very interesting.
Yeah, I congratulate you because you made a very serious work, that you really made us believe that we could build this now, today. So you're really self-assured on the research you did, and because you mastered the research you did, you feel able to propose new forms and new geometries, which seem, you know, credible and that could work. I have a question which is maybe completely out of the spot, but how does this work on the rain?
Microphone.
I mean, we didn't go that far, like specifying materials, but no, but I mean, we would need some kind of aggregate in the clay or some kind of treatment, or maybe even we discussed this in the beginning, using straw on top of the clay surfaces, or I mean, I don't know, like this is really not very well resolved. Yes, through most of the year, yeah. Yeah, we would need to work on that.
Yeah, because you have problems with rain because your structure would be just melt into the earth back. And also because such an openness doesn't work well with rain and wind all together. So this lovely couple that are living here, they should hide in the bathroom probably, or something, or be okay with rain. But I'm getting into critics on the distribution and on the architectonics, because the concept is very nice and very appealing. So I would like this to happen. Yeah, so I really suggest you to, to really think of if this is okay with the amount of rain in tropical climates, because maybe it is not. And then we don't have to think of this material like appropriate for that climate condition. And we have to focus on the appropriate climate conditions. Yeah, we need to fix materials. If we want to build in kilometer zero materials, then we have to pay attention to the existing climate conditions. But yeah, it's an amazing space you have created. Thank you.
Just react on that. I thought that actually you were using also bamboo and wood because of that, because of protecting earth from the rain. Since you were talking about a bamboo facade and a wooden facade, I was interpreting this, that you had this outdoor shell of water-resistant material, and the earth was more on the inside. And since we got to know that it was not the case, maybe it's an idea for developing your concept. Beside that, I think it's a very interesting project. I think you really nailed the fact that ventilation is key in this kind of climate, and I think from a design point of view, it has a lot of interest. Maybe intimacy would be one of the key factors that we should think of, since we see that everything is open and the different buildings are so close. Beside that, yeah, and the water resistance. Beside that, I think it's a very good project.
Yeah, a very quick comment from my side as well. I compliment you for the design qualities of this space that you have created. I think it is fantastic. It is also like very nice, especially in the last render, when I mean here as well in the section, but here they look all pretty more similar, whereas in the render they start to appear in kind of almost different scales as well. And I think no, they're of similar scale. Okay, but it somehow felt that this could become a kind of like a village, and could become a kind of an urbanization within a tropical climate that could be really interesting when you started to say how these platforms could start connect among the different levels or among the different buildings. And I think that, again, as I was saying in my comment in your previous part, this idea of having a system, and that system could give you a variation of results according to the size that you need, according to the height that you need, etc. Because I've been to Thailand, and because I've been to Indonesia, and because I've been to the green villas in the green school, I know that people, and because I've lived in a place like that, I know that it is very, very, let's say, normal to be in such open spaces with no intimacy, because when you are, I think that you nailed it when you said that you're doing this for two people. There is a lot of culture of living like that there. So this I wouldn't mind. It's part of the culture. I think that the fact of I mean, the criticism in relation to the rain and to the water, I think this is I mean, it's been an issue that for many years we're dealing here with that material. There are a lot of different solutions of bio-based coatings that they could protect this material. And of course it requires maintenance, but I think those are, I mean, you cannot just say that we haven't thought about it, because there are solutions. And I think you need to be able to defend that when you are doing a building. It's not like, oh, we haven't felt the rain. No, that's not true. I mean, all of these things, they are outdoors. So you did think about the rain, right? And I think, as I said, there's a lot of different hydrophobic solutions that could be coated on that material, that they are bio-based. Of course, this requires a lot of maintenance and like frequent applications of that coating, but there are solutions. Exactly, bamboo as well needs maintenance, and And I think this should also be part of your narrative as well, no? Thank you. Beautiful work, very beautiful. We would like to live in a place like that.
I pass you the microphone, but then we'll go to the next group. Geometry is another way, no? To actually channel the water in specific locations. I think that is something that you are starting to touch. And I don't know if it's really an answer, but I think that there is something that goes in that direction. I'll give you the microphone, but just before that, I also wanted to salute the fact that you've taken a climate that is very difficult, because a hot and humid climate is a climate in which you don't want massive buildings, no? And when we look at everything that we have around us, Earth is a compressive material, it's very heavy, you need to work with thickness. And I think in your case, you've gone into a project that is really light, and I think it's very successful in that terms, but it's somehow difficult to be conscious of it. But that's why I wanted to say it, because I think you've actually created a project that nobody in the OTF before has actually really looked at. And I think you've done it with a lot of, providing a lot of answers, and I want to congratulate you for that.
Yeah, I agree with most of the comments that have been said, especially the water effects on the structure. I just wanted to touch another aspect that is, see, we are in a 3D printing course, and obviously you really challenge the geometry to achieve this main structure, and combine it with a lot of, let's say, industrialized elements. I mean, the beams and timber and everything that has to be built on site. But maybe what I maybe miss here is that you really used a lot of other elements with really complex geometries, like the staircase, or even this bamboo grid. That I understand that for architecture issues you prefer to use bamboo instead of 3D printing, but there are a lot of elements with a very complex geometry that could be really interesting to explore in the 3D printing, especially this central spine with a staircase, etc., which is in terms of geometry, it can be really interesting to try a little bit the complexity of it and 3D print it. We just.
Thank you, Guillem. So we continue our trip around the world. Let's leave Thailand and let's go to Barcelona.
Yes, hello again. We're going to present our project 152 Travesera de Gracia. And as Eduard mentioned, our project is located right here in Barcelona, right next to Travesera de Gracia, in a plot, an empty plot that most of us might have crossed. And building in such a context of a high density residential neighborhood can be quite challenging, whichever construction process we decide. But 3D printing offers a rapid way of construction and the freedom to tackle specific formal challenges. In addition, 3D printing with earth, due to the proximity to the material, the fact that it can be recyclable and the precision of the machinery ranks it as quite sustainable compared to other traditional techniques such as casting concrete.
So we are in Barcelona, and Barcelona, as you all know, is a city with an intense flow of students and workers seeking for accommodation and affordable accommodation. This is why the project is a student housing, emphasizing the verticality because of the plot and presenting 6 different floors. Barcelona is in the Mediterranean climate, and this climate presents a lot of, present mainly one climatic issue, such as the temperature fluctuation between summer and winter, and the difference temperature during the day and night in the mid-season. To solve this problem, the main strategy is to maximize the solar radiation in winter and minimize in summer through horizontal shading to south and vertical shading to west and east, and also integrating these strategies in the 3D printing, as you can see in the right image, in the design of the elements. Another strategy is the use of the courtyard, classic feature in the Mediterranean climate. During the winter, used as a greenhouse effect to produce this greenhouse effect, and during the summer for the ventilation and also to bring the light down to the bottom floors. The last climatic strategies are to protect the top floors, so the top ceiling from direct sun radiation through air cavities, and also to increase thermal mass in south and north facades. And in 3D printing, to use these cavities also as a mass insulation or services.
And as a reference of what it means to build in Barcelona, we have Casa Batlló from Gaudí, which he integrates the courtyard as a climatic feature and as well as the central circulation. And in the section, some interesting features, we can see how he tapers the inside facade and also how he changes the colors of the tiles from blue to white from top to bottom, balancing the light that reaches the building from within. And putting the staircase on the central courtyard, it allows us to manipulate not only the circulation, but to manipulate the way we conduct the light and the ventilation throughout the building. And in these explorations, we try to understand what it means to actually 3D print a staircase and how this would touch the courtyard and the structure. And the structure of our building is based on these 3D printed vertical and horizontal elements, and the distribution of these elements, these vertical elements, has consequences on the quality of the spaces. So the bigger you have the spans, it's a challenge, but you have bigger spaces within the building. And due to the constraints of the material and the technology, most of what is done today in 3D printing, as we mentioned, is the vertical extrusion of walls. And derived from our research, our support system allows us to print cantilevers, which as a consequence allows us to do floor plans, which is actually very necessary when going high. And as a final distribution of our structural system, we have this distribution of these columns and vaults with our spacing between of 12 meters square that we seem appropriate to put in a dormitory for students, and also having this game of separating the columns, allowing for circulation within this facade.
So once the structure was established, we looked at incorporating the staircase on the sides of the courtyard in order to minimize the blocking of the sun coming down and optimizing the ventilation going through. So we extracted the vaults from each floor and created the surface on which the stairs would lie on. Coming back to the site in Barcelona, it's typical to the city where it's long, narrow, and ideal for vertical building, which poses some questions as to which machinery we would use in order to print. So the WAS crane seemed promising as it's derived from a traditional crane and is a modular system which enables to print with multiple machines simultaneously. We made some modifications to the arms and the height of the machine in order to suit our site. Which is about to come on screen. So here you can see the 11 machines that are distributed across our plot and fit perfectly and allow to print from the adjacent walls in 180 degrees so that we can maximize the printing area of our plot. And this grid is then used to distribute the floor plans and incorporate our solutions. So the printing strategy and the process of 3D printing on a plot, we don't imagine being too difficult. First, the machine would be delivered, then the material would arrive to the site and be stored on tanks. This would then, the printing process would start, and once the first columns are dry, the support's inserted, then the vaults, and this process would be repeated from floor to floor until the building is completed.
And the process of printing would take place quite continuously with all the machines operating simultaneously. And using the 30 centimeters rule from WASP, which we can extrapolate, they're going to be improved over the next years. This would take 75 days to be built, a building of this size. Yes. And the lines of the structure derivated from these vaults connect to the columns, and we segmented these 4 sections of structure, and this is how it's distributed. And these structural segments, they respond to climatic fixtures. So on the south facade, allow for balconies, and at the same time, around the courtyard, allowing for circulation.
So the ground floor plan presents more public feature compared to the other floors in the building. We have the bike racks and the reception to the north facade, and the vegetation present in the middle of the building let's say, with the function of greenhouse effect during the winter and the ventilation to cool down the temperature during the summer. Going to the common areas, we have the living room part to the south, taking advantage of the best daylight throughout the day, and the kitchen and the dining room to the right, to the north. We have sleeping areas as well. We accommodate 8 rooms, 12.5 square meters each per floor plan. And in this case, differentially, unlikely the common areas, we have the the private balconies to the north, and the common areas, we have the shared ones.
So the section integrates these climatic strategies as well as this vault structure. And we can see the distribution of floor plates with shared spaces intercalating with dormitories. And we can also notice how the columns, they shrink in size from bottom to top, responding to the load which are submitted. And also using the same strategy, the tapering of the interior south facade, and the use of the upper space as a terrace that can be used both in winter and summer, following also the climatic strategies. They'll have this textile at the top that can be extended during the summer and be open during the winter. And we can also see how the infill is used to create these shapes. And these vaults are integrated in the facade, creating the language of the building. And this will be the facade to the interior block to the southwest, and the facade that faces Travesera de Gracia and where the access happens, with these balconies on both sides.
So finally, responding to the climate, machinery, and structure of the building, which is continuous throughout the columns and bifurcates into the vaults, we create a unique living condition for students in the city. And we believe that with our structural system, our support system that we've created, we can develop a new architectural language that doesn't seem too far away from the present. Thank you.
Thank you for your presentation. Something that I liked related to what you presented before is if we go back to the render of the construction process. Yeah, I like that because it's curved. It's curved, and it links back with what Areti was saying, is that there is much more thinking in the form itself in terms of not making any angles where that could crack, and having it maybe flexible so that it moves when the earth contracts as well. So I like this kind of forming much more than this one. And another question that I had is, how do you make the link between the different machines? Like, how do they connect? Like, how those printings are connecting to each other? Is there any interferences between the machine printing at the same time? Is that going to be prone to cracking? Have you tried that to print in two different areas and making the link? Because it seems that you're facing a case here that you haven't faced there.
They just finished, I don't want to promote WASP, but they just finished called Tecla House in Italy by WASP, and they were printing 2 houses at the same time, and they were synchronizing the printers. And here, of course, we need more than 2 printers, as we said, we need 11, right? But yeah, I mean, I think it's possible, let's say, to synchronize more printers. They demonstrated it with 2 printers.
Better when you try, if you print the process. If you print everything at the same time, you have less. The 20 years collision,
We didn't study the algorithm though.
I'll just add that it's very exciting when you have 10 printers, no? When you solve that problem with 2 printers, because 3D printing, if you have 1 printer, it's relatively slow because it's 40, 50 centimeters a day. But when you can work with a horizontal surface and have a lot of printers, you can actually be very efficient and very fast. So it's a very good question, and it is solved, which is great news. No?
So I have some mixed feelings about this project, because on one side, I find it fascinating that you managed to use this new technology within a block of the example, within buildings. I find it brilliant the way how you combine the crane to make actually to cover all the surface. And I find it also fascinating how the plan looks almost like a normal plan. But at this, so like yeah, I mean, like the way we've been building up to now. But at the same time, this is also my concern. No? I mean, there must be something strange if we change totally the technology and we end up having a normal plan and a normal facade. No, I think you should go back to La Pedrera, check it twice. Because clearly, I mean, we are all impressed by these images and by the, as you said, the axonometry, which are super inspiring. There is so much intensity, but then we do not see this intensity and this potentiality transferred to the plan and to the facade, which still is a good news because it means that you have some room of improvement, which is super exciting. No? So I think that, as we were saying, no, the idea of finding this aesthetic or sorry, my sister is calling me, and finding the, she never called me, and finding, Areti was saying, find the, how you use that nice expression, find this way of being, or what to say, finding what it asks to be. Yeah. Yeah, let the matter be what it wants to be. So I think you found it in this perspective, but there is still a bit of research to be done in the plan and in the facade. Also, at some moment you say that you're gonna, the pillar are reducing the size, right? You said that, but it's not on the drawing. So just in one side, there was just one on one side, and all the other was not. I challenge you. I just see it on the right. Anyway, it's a detail, but I mean, is it in the sense, let's embrace the dynamic of the forces and the dynamic of the construction instead of constrain them to our preconceived idea of how a floor and a facade should be. You know, so let yourself inspired by the fact that, okay, I have less load to bear, so I'm gonna make super thin walls because here I don't really see it. So on one side, on the facade only. And anyway, do you get my point? Because that's the idea, no? So let's look for this excuse to actually let the material and the technology express, okay? Okay, thank you.
I will jump the whole discussion of what has been said in relation to the aesthetics that goes hand to hand as an emergent, let's say, new way in relation to technology, to the manufacturing technique, to the material and everything. I will not speak about that because we have been talking about this until now. And I want to raise the point here of, especially because you are in Barcelona, and you are in the plot, the typical plot of Eixample, that either a steel glass building would be raised or a concrete one. So I think that in this case study, more than at any other, it is very, very helpful to start having some kind of data and information about the difference that such a building would make in terms of economical impact, environmental impact, time of construction, complexity of construction and all the alike. Because I think that this might, get back to you with the kind of information that might require from you to simplify even more. No, so maybe it would actually get you to be even more alike a traditional building, so that you can reach, the same or similar, let's say, numbers of at least the cost, no? Because it's clear that the environmental cost is something that you will lower. But what about the monetary one, and what about the time that needs to be put into that? No, I think these kind of data would be really helpful to have here.
Well, congratulations once again, another very interesting project, and you really worked well on every details, I think. So well done. I am on one side, I'm really fascinated about this modernist architecture 3D printed with earth. I think it does, as images, your pillars, your organic pillars have a lot of power. On the other hand, from a structural point of view, I think it's a bit optimistic to think that we can build with earth as we build with reinforced concrete. But this can be actually something interesting, because it can bring you back to what Silvia is saying. So earth is not reinforced concrete, it works in a different way. It works more like a traditional house typology in the Champler, as Arati was saying. So maybe if you really listen a bit closer to what the material is saying, you will find a different organization, a different structural organization, structural design, and also a different floor plan organization, and so on. So yeah, maybe tune a bit more on what is the material structural performance, and it will also lead you to an aesthetic that is completely different from what we have now with reinforced concrete. So it's I think it's a challenge, but also an opportunity to develop it.
But I feel that the critique is almost that you are almost too realistic. Maybe that's a big shortcut, because there is definitely a lot of very useful comments in order to develop that. But I think what the project does in a very good way is to bring the comments that Areti is making, of okay, what's the cost of this? How can it compare to an existing building? The density that you've been working with that's what you've kind of taken as a challenge to be able to make a building that can be compared to the rest of the city. And I think for that, the research you've done here is very, very valuable. And I think it raises many questions that I think what I would propose to do is that we go to the next project, because some of these questions that you're raising, I think will be also applicable there. And then we can also then conclude on a final discussion after the next group. Yeah. So thanks to you guys. And our next stop is going to take us to Botswana. Yeah.
Okay, good afternoon, everyone. We are here to present our project called New Hansi. So we started our project asking ourselves, how can architecture act as a medium to incorporate a hunter-gatherer community into an urban area while respecting their traditions and heritage? Another question that we asked ourselves was, how can 3D printed clay provide a sustainable housing in a hot and dry climate? And how can a partition wall create an ambiguous dialogue between the inside and outside space while respecting the comfort of the user? So introducing the San people, the San people are a nomadic tribe of hunter-gatherers found in Southern Africa who are expert in the desert ecosystem.
So the challenges that are being faced at the moment is that because of the new anti-poaching laws, we find that the San people are being moved from the central Kalahari, and they're being moved into settlement camps, such as Mikadi, which is the camp that we're looking at, and Hansi, which is 1 hour away, is the first stop that they will take. So the spatial heritage of these of the spaces that the San people create are clusters around the courtyard with circular forms, which are optimized according to the hot and dry climates. So what essentially happens is the outdoor space translates into, the courtyard translates into a lounge, and this is what is then considered the outdoor space. This project aims to serve 50 San people who would come to form 3 different communities, one of 25 people, one of 2 people, and the other of 3 people. Excuse me, let me say that again, 25 people in one community, 15 people, and 10 people in the smallest community, which makes an agglomeration of 50 people in total.
So the climatic challenges that we face in this region are, of course, intense heat, large temperature fluctuations, high solar radiation, low wind speed, and high glare. And the way to embrace these challenges is we develop different strategies, such as increasing the ceiling height for the hot air to rise, increasing the inertia of the ceiling for passive solar heating, achieving climatic stability by sinking buildings into the site, and also the use of courtyards to create microclimates.
So the Botswana Housing Corporation typically provide housing for the San communities that would be coming into the urban context. And so what we find is our site is located between this housing because we'd like to sort of provoke this, this notion. We find that the housing proposal, which is quite typical in a Western context, which makes sense because it's colder, doesn't make sense in this context because you have small patios, which doesn't represent the social infrastructure of how the San people live and how they spend most of their time outdoors.
So to be able to encourage collaboration between skilled labor and a technical workforce, we therefore choose to select the WASP 3D printing crane. And this is because it's a light and affordable and easy to deploy construction technology. We also envisioned that it will allow for a labor force that will receive a transfer in skills, and it will enable community participation during the construction process. We also selected this WASP 3D printing crane as the appropriate technology because it's capable of supporting the communal way of living of the San people, owing to its capacity to be arrayed into a network of 3D printing crane arms, which can print clusters of geometries at the same time. Additionally, the dimensions of the WASP crane allowed us to be able to generate a grid, which eventually served as anchor points for the network of 3D printing crane arms. And also during construction, they served as centers for the location of walls and 3D printed domes.
So there are 5 types or 5 scales of courtyards that we'll be using in this space that essentially make up the privacy gradient from the public to the private. The smallest courtyard that we have is 2 to 4 square meters for a couple or a family of 5 people. We have semi-private courtyards, which are 9 to 12 meters, such as communal dining areas, as well as playgrounds for the kids that would be allow for visibility from the kitchen. And the 3 communities have a courtyard that would grow desert ecosystem foods such as medicinal food, nutritional food, as well as mystical plants. There would also be an educational courtyard with recreational and lethal protected plants in order to preserve the knowledge of the specific context. So the primary courtyard houses the ceremonial rituals such as weddings and social gatherings in the space. And this would be where all 50 communities would meet. So the system that we used for our distributions or that we're using is from the central courtyard in order to connect to the community, the 3 communities. You move into the 3 communal courtyards, which then connects to the communal dining. This further connects to semi-private courtyards, as well as the circulation parts from private spaces. These then start to link up to the kitchen spaces, which is the first sort of contact with a physical built space, as well as the lounges and patios, which are more public areas. Then you connect eventually to the bedroom, and lastly to the private courtyard, which would be in each individual home.
So the design of optimized openings in a performative wall brings in diffused wall, diffused light and reduces the glare. It also allows the ventilation by having a thickness to opening ratio that compresses the air. The number of wall layers creates thickness, which gives inertia, complementing the passive solar heat during the cold winter months. The curved walls openings in the wall creates the illusion of lightness, which blurs the lines between the outside and inside. The wall is staggered according to privacy needs and frame views.
So in plan view, we layered the spaces according to a privacy gradient, and you'd have to go through certain realms in order to get to the most inhabited space, which would be on the inside. Because as we know, it's super hot, so we want to kind of create a microclimate or more habitable interior space. You would pass through spaces such as the playground, the foyer, and dining in terms of a built space before you would get to more private spaces like the bedroom or the kitchen, which people actually would spend time in. We then put our distribution onto the site itself as well. Connected with the idea of introducing the footpaths onto the sites, connected to the 3 communal courtyards that would then connect to our kitchens as a spatial relationship diagram, which then connects to our lounge, our bedrooms, our private courtyards as well. And finally, then we then translated this into the grid by placing our domes first, where we have larger spans, and this would then translate into the actual 3 communities. So what you see is the first community, the second community, and lastly, the 3rd community.
The established privacy gradient was also used to define the position and porosity of walls. So we started out by mapping desirable sightlines onto the program of spaces which we then use to establish zones that would have porous walls to let in light and views, as well as areas that would require solid walls to maintain privacy and provide climatic mass. Okay. And in terms of the construction of the project, it's envisioned that it will be built in 3 phases using 0-kilometer materials. And in this case, the courtyards would also have multiple purposes. In the construction phase, they will serve as places where material is stored and mixed and redistributed for construction. In the second phase, this would involve the setting up of a network of crane arms that would 3D print walls and domes. And the third phase would involve the setting up of locally sourced timber gum poles to put in place a structure that would accommodate a flat 3D printed clay roof. The final completion of the house would involve compacting of a polished clay floor, and after which the house would be ready for habitation.
So this is a little bit of the construction process that we envision, involving as well the local people to do the manual work and to get the materials from the site as well.
So when we look at the section uses the climatic stability of the ground in order to create a more stable temperature. And essentially by sinking the buildings deep into the ground, you get more stable temperature as opposed to the high fluctuations that you get during the day. We also sunk these spaces according to the relationship to the untreated air or the hot air. So if we have a microclimate such as the courtyard spaces, we wouldn't necessarily have to sink it. But then when you have spaces that have contact with the outside hot air, we would then sink it in order to maximize this opportunity. The winter sun angle, well, we also designed according to the winter and summer sun angle with small shading to avoid the harsh 86-degree inclination of the sun coming into habitable spaces, and also provided patios in that regard. But in the winter time, when the sun is at a lower angle, it comes into the microclimate courtyard.
The roof spans and the grid were also a response to structure and climate. So we made use of locally sourced timber to serve as a secondary structure to support flat clay printed roofs. A dense radial network of locally sourced timber beams with 1.5 meter spans supported on clay walls, and making use of 50 millimeter diameter timber gum pole columns were combined to form spans that would provide shade to clay printed walls. We also were able to create an interplay between different types of construction technology, where we have these optimized performative clay walls of various porosity and thickness that are able to allow in light, air, and ventilation, while still being able to create an ambiguous dialogue between the outside and the inside. And at the same time, still integrating vernacular construction technology to complement a very contemporary and performative construction language. The porosity of the wall is able to create an ambiguous dialogue again between the outside and the inside, where the spatial relationships are translated to a privacy hierarchy, with the most habited spaces being in the interior. All the spaces have a relationship to the interior courtyard. From the bedroom, with the diffuse morning light, you're able to look into the lounge and the courtyard with a constant dialogue of diffuse and direct light throughout the day.
Okay, so in conclusion, we believe that the courtyards are not only cool spaces, figuratively, but literally, where the climate would be moderated between a group of buildings. The project combines technology and the heritage for a new SAN housing typology that is based on clusters around outdoor activities with microclimates in a hot and dry climate. Using 3D printed architecture with clay openings in walls and clay roofs, the housing is optimized in terms of ventilation, heating, cooling, while adapting to the needs for privacy as well as visibility. Thank you very much.
Thank you very much, and congratulations for the project as well. I will make this comment, but I think it's a comment that could be applied to all the groups today. But in your case specifically, and I think that maybe because I'm sitting here in this point of view, until you showed the first render of the construction site, I was seeing a perfect combination of your project with the wall with the project of the vaults. So I see that these two projects from my seat. So I was seeing the plans, the evolution, the distribution, the combination of these different centers, the courtyards, etc. So I'm not saying that it's frustrating when I saw this, but I said, oh, it's a pity that you don't collaborate a little bit more between groups, because I think this was a perfect case to combine both systems. But as I said, I mean, this is a kind of a clear example of this, but this could be also applicable to other groups. So maybe I see that the use of the 3D printing that you are doing for privacy, this transparency, the walls, etc., is really nice and really interesting. But I would say that it would be much more powerful if you combine efforts with the rest of the teams.
Thank you. I actually agree with you totally, and maybe it's more a comment for the directors, or I don't know how this program was shaped, but I really love the idea of having like different climate and different buildings conditions. I think though it makes it very challenging for this group, for example, that is trying to treat light, and it's such a specific aspect of a building. So try to integrate that into a whole building side makes them shift away from their specific thing, you know. And I don't know, maybe if there were, the four groups were actually presenting their work applied to every single location. I don't know how that can work, you know, with the logistics, but it would have been very interesting that a group actually tackles the issue of the structure that links back with what you're saying. And then how do we heat up or cool down the place? So that's the other group. And how do we, you know, have privacy and light, which addresses the question that I had originally with the privacy. I'm glad to see that in the community aspect, because that's very important. So yeah, I couldn't agree more with the fact that architecture is all about those different fields. So it's difficult for you guys because it's only about light and privacy. Another thing is that I really like the community aspect in your project, and which raises the question of using machines, you know, while you're building. So I understand the value for the community after it's built, but I come from a construction field where we have 50 people on the job site, students, volunteers, and everything. And that creates such a community while it's being built. But it doesn't mean that 3D printing is not allowing that. And actually that makes the link with a comment that I have for all the groups, which is that something that we don't see in every presentation here on applied cases is the amount of work that's necessary to actually gather, filter, and make the mix. So I know that every group has put steps, you know, like you excavate and that, but that's most of the work actually. The printing is allowing very interesting complexity in the shape, but I like the community aspect that links with the fact that there could be community on the excavating work, the filtering work, the mixing work, because you know we need to add sand sometimes, we need to add fibers and stuff like that. So that's a huge amount of work that can be done in a community aspect while building. If we go back to the previous render, which is being construction, Yeah, that was right there. Like, it's empty. How many people are there? Like 5, 6, you know? I want to see what's happening like right next to the job site where there is excavation, filtering, mixing. And I mean, all of that requires a lot of, that's a comment for all the groups. Yeah. I think you need more people than that. But that's a more general comment about every presentation and every group is that, you know, you cannot really order clay in bags like that if you want to be 0 kilometer. You need to actually do a lot of work locally. Thank you.
I'm gonna build up on that. I share the comment about the community, also because your project is about that. And maybe I missed some more insights on how the community is actually organized and why this community, this society or this community needs all these layers of privacy in the organization. I think that if you have this, if you can add this, would make the narrative much stronger and you know, round and round, yeah, and understandable for everybody. But I disagree on the fact of that this project is missing an opportunity in not taking advantage of the other technologies that we explore today, because I think that is what I love about this project is that you carried us about through a journey, making us feel and understand all these different layers of privacy within the community. And then we just, one detail, which is the one that you presented at the beginning, you solve it. And you managed to make building an entire village with a detail in a super simple, relatively simple conceptual proposal, but super effective because with just this detail, thanks to the fact that this detail is allowing gradient, you manage to resolve all the relation between the different components of the construction. So in my understanding, the most brilliant part of this project is the simplicity. The fact that with this detail and its gradient, you can have all the possible combinations, which are pretty complex, of relation within the community. So I really love it. I find it brilliant. Yeah, thank you.
Yeah, I also like very much your project. Actually, it's the only one that has tackled living together because the other projects we saw were single isolated houses or maybe a group of houses together, but not having a community. So it is very interesting to me that you are addressing the shared space and all these gradients and this very serious approach of the needs of every space in terms of transparency or privacy. This is building a community, this is building a city, or, you know, so that's more complex, and I appreciate that. And connecting that with your layers of transparency is very wise, because actually it's what the difficulties of living together is how much do you want to share with your husband or with your kids or then with your neighbors or even, you know, so it is exactly this level of transparency, the amount of space to share, the amount of space on your own or only for your family. So I think it's very nice that you started with this issue of the light, but your device, you also mentioned when you were presenting it, you rapidly turned the discussion into the transparency. When you discovered these layers, while you were designing that, you discovered this capacity of the layers of providing transparency or privacy. And you have just exploded it and use it for your design. So I think it's a very nice project. I only have one question now. You were mentioning about the amount of earth that needs to be removed and so on. And then I saw, so I wonder how big, I mean, can we use the removed earth to create these courtyards in the middle, or or we need like 10 times more? Or is that part of your project? Could you tell me about that?
Okay, so first, to be able to respond to Guillem's comment, there's a degree to which this architecture is a hybrid of some of the different strategies that have been unearthed during the research. So the walls in this project make use of the porous wall system that we've developed, but to be able to also respond to the climate that we're in, we require inertia in the ceiling plane. And the construction technology proposes a dome that's able to encompass inertia within its cross-section, but also allow for larger spans in a context that initially was very limited with regards to the kind of spans that they were able to achieve in vernacular architecture. So to a degree, there's that synergy between the different types of research that have taken place this year. Also with regards to, sorry, I lost my train of thought. With regards to the material phasing, and also as it relates to the construction technology and the use of locally available labor. In this project, it's envisioned that there'd be a very close collaboration between these two aspects, being able to make use of something very contemporary and cutting edge, but also still being able to incorporate the heritage of building and the technology that this specific context has. In fact, based off our discussions, what we were able to see was that this project would actually require a larger number of local skilled labor to realize, because they are the ones who would have to carry out the excavation or to provide manual labor that would allow for the movement of material. And in this case, the ratio of skilled technicians to local labor was going to be about 1 to 6, where we envisioned 30 local skilled laborers being able to provide their skill set, but being supervised by a small number of trained technicians. So there's a bit of that give and take, whereby this project still requires a large number of people to realize, but it allows for this interesting collaboration between two different worlds of technology.
One important bit that also passionate us about what we see in Africa and all the projects that we see is not, as you said, just an experience of digging and moving things that is more labors. But we believe this is one texture or one aspect that we see, but there's thousands of work that need to be done on finishing, on adapting, on touching. It's a material that is not fixed. It's easy to excavate, to add more, to add another layers, to paint it, to give it vibrant. It's not something we're controlling digitally, but clearly it could be a framework for people to then take and to modify and to change and to adapt. And so I believe the community of people that will be working on these materials and on these elements, but that's our hope. The technology doesn't like split between there's the people, the technician from one side, and the other side there will be like the brute force workers, but they will be a much more integrated manipulation of, okay, we can mix especially for this machine. Hopefully the tools that we're manipulating of digital design could be more accessible and more easy to integrate in phenomena of co-design together with communities. Bit of the work we're doing actually with Elisabetta and some of the people here in IAC, trying to see how these tools can involve people in the design. But we believe also the construction side could be not just providing the machine, but also finishing with the machine or after the machine in all these elements that you add as well in your renders. No, so I think it looks very split, but we hope it's just an enhancer of architectures and collaboration in these elements. So a lot of potential.
I just realized we didn't answer one of the questions to do with the amount of material that is available on the site, and would it be able to print this amount of housing? I think this was one of your questions. And I think that as much as we don't have specific numbers, but what we understand is that by excavating from the site, we could calculate a proportion of how much we sink the building into the ground, for example, in relation to how much material we might need in order for it to be not only outsourced. So, yeah.
And I wanted to add something from the comment that you were making. No? It's been now 2 or 3 years that we collaborate on this project with UN Habitat. I think the first time that we asked the question of whether it would make sense to build with this technology and this material in Africa was 3 or 4 years ago. And at the beginning, we were a little bit skeptical, no? Thinking, okay, bring a technology that is pioneer, that is complex, that is robotic, that requires really kind of trained people, to a context that is really far away, where there is actually more immediate needs, it seems, was a very provocative question. Somehow, some students 3 years ago decided to work through a project like that, and for a refugee camp in Kenya, and kind of demonstrate that through the bringing of a complex technology, they would actually enable to propose a new building technology and a new housing typology that was much more connecting to a local culture, as you said, and also to potential local community in terms of the way that they are organized socially, their lifestyle, which I think you demonstrate really well into the project. And so I think that the way, somehow the critique that they do of these existing houses that are being built now at the moment, that are totally based on a Western model, don't consider how families are being deployed, not deployed, are being formed over there, is highly questionable, no, that model. And I think that through yours, you even with a kind of provocative move of bringing robotics to a place that is so far away, I think you managed to use it as a kind of activator that then enables a lot of qualities to take place. And I think that the master plan that you do of this project, that is I think it's a very beautiful drawing, because it's a drawing that actually really considers how people live, as you were saying, in relationship to each other and actually share spaces. And I kind of have no doubt, because I followed you in the working process, that it is questioning about what this technology can offer in terms of how do you work with it, how do you question existing plan layouts, existing living layouts, that has actually led you to create connections to many parts of the culture that otherwise seems to be really lost, no? In many places, actually, in the context of Africa, with the huge housing crisis that is going on there. But I think potentially in all parts of the world, and I think in all of the other 3 projects that we saw before. And I think this is really reassuring and really good to see that it's not about the technology itself, no? It's not a self-referential project. And I think this is what we try to do in the program. It's about how this can act as this can be an activator in order to open doors of architecture, doors of construction, that sometimes other processes that are much more automated, much more efficient, seem sometimes to have closed, no? And I think as much as often we see that 3D printing and other robotics is kind of opening again the doors to craft, I think you demonstrate that it opens the doors to many, many, many other things. And when I see a project like that, I'm totally confident that you can go to Africa with robots and you can actually really improve a condition there. So, and I think it's very successful in that sense.
Yes, let's go to Africa with robots. Well, first of all, well done. Really, it's a very interesting project. I'm really happy that you managed finally to do one thing that I think we've been trying to do in OTF last year as well, is to blur the distinction between the wall and the opening. And this is a great potential for 3D printing, I think. And you managed to do it, and to do it in an interesting way, in a way that makes a lot of sense, talking about ventilation, which is a key factor in this climate. So this is great. I think another big achievement of this project is finally this. You've been thinking of what does it mean to have different cranes, right? These cranes, they are really actually limiting your floor plan, and it means that you will have to build in hexagons or circles that are one next to the others. And this is a big limitation, and sometimes it can lead to some uncomfortable situation. Like, I don't know, I think in the tropical project, for instance, I was like, oh, these tree houses are a bit too near, and this is because of the crane maximum distance and stuff. And here I can really feel it makes sense. It is actually an opportunity to say, okay, we are living one next to the other, but this is actually a plus, because the interspace in between the different houses, it is the most livable and the most living space of all. So these two things, I think they make a lot of sense. If I can be critical on a point, I think you really worked well all of your concepts, and we had a lot of interesting diagrams. And I think you were a bit shy on the architectural side, on the design side. I was waiting for this render for the whole presentation to finally see what does it look like? What is the quality of light, which is one of the main key factor of your project. And you all have this great tool. I mean, you can really have a render of all of these different spaces you can design. I think you can really explore more about it. And I think if you would have pushed a bit more on the architectural design side, you could have found a lot of possibilities. For instance, this gradient that you have, which is super interesting. Maybe it's not just like one wall is open, one wall is less open, one wall is closed. Maybe you can have in the very same wall, you can have a gradient of opening or openness, right? Or for instance, about the community inclusion, which is a very important problem, and I think you solved it quite well. For instance, all of the traditional buildings that you showed us, they had a traditional and very smartly designed roofing system, right? And maybe instead of having something that you maybe put together, put a bit on top of it, maybe you could have something inspired from that. And this is also a way to include the local community in the project, right? I mean, many things that I think once you start working on the design of it and really having drawing it and modeling, I think many ideas can come and can enrich this project that has a very good and strong starting point.
Thank you for this comment. Yeah, and I wanted to bring clarity towards what I said before. I'm not criticizing 3D printing at all. I think there is a huge justification with the fact that we are trying to create complex shapes. You know, you're talking about gradient. I mean, how do you do that without a 3D printer? It's difficult. So there is a huge justification for 3D printing. And I think also that it just shifts the labor, especially if you're printing with earth that requires so much processing before that actually all of those people that needs to be worked, we're not replacing labor. We're just like shifting it towards the processing before. So this community aspect while building will be maintained. And, and since we are trying to be environmental friendly, something that would be great to investigate as well, that links back with what Areti was saying before, is what is the life cycle assessment of a building like this? How much kilowatt hour do you need to run this machine versus all the concrete industry? You know, like take the whole building and let's say I'm a client, I'm asking you, why would I go with this and not concrete? You know, just I'm ready to hear that it's more environmental friendly, but I want numbers. I want to know, like, versus concrete, what are the you know, the embodied energy of this compared to that? What is the value of using local labor instead of remote products that are coming and you know, having everything processed with a machine? All of that, it would be nice to have like a overall picture of the difference in terms of energy and emissions.
Take advantage of your point. There was a comment on the Zoom account as well about the water, no? So how these elements are also consuming water in the processing and the things. And they was asking if, in the context of Africa being lacking water, how we will actually maybe make it worse. That actually, if we look at all the type of constructions, they also consume water. Most of them is concrete and they use the same amount of water or more because they're more liquid, let's say, in the way they cast it. So we're not so impactful. Compared to concrete, the order of magnitude is 10% of the CO2 well, let's say if we emit 1 ton of CO2 for each ton of cement, we emit here much less, like 100 kilo. So we'll be 90% saving in terms of CO2. The machine itself, hopefully, thanks to the collaboration with WASP, but also the development we've been doing here, we see that potential to reduce the impact on energy. It could be based on solar panels. It hasn't been proven yet, but that's the goal, that it can go this, as well as the tools to be able to be open source and share with people so that they can also hack it and fix it. So more Linux approach than the Apple approach to technology. So trying to empower with the technology. We're not yet there, but there's clearly potential. But I promise you better numbers next time. Homeworks here. I think it's amazing. Kunal?
Sorry, I had to jump in because I heard a couple of times that the use of machine brings a lot of complexity on site. I just don't think it's only an impact of shape. If you look at some villages, I don't know if in Botswana is the same, but in India, how the villages are formed is that each community makes their own kind of an barrio and they live together. So probably a new system, let's say in this case we call it a machine, is kind of adding a new culture to their entire sociology. So I think in a way it has a huge social impact, which still we have to go on site and probably check it out. But I think there's a huge social impact rather than just making shapes, which is kind of let's say has a good reason as well, because every tool, or let's say most of the built environment that we see around us, it's a reflection of the tools which were available. So now that we have such advanced tools, why should we keep constructing normal houses, which we generally see with, let's say, I will not take names, but there are some houses which are made out of concrete, which can be done in other ways, but it's much faster. So I think it's a huge social impact, also gives an opportunity to design. So it's empowering the people who are actually using. So I think it's nothing to be underestimated, the social impact of having a new thing inside a community. It's always very exciting. But
great, that's a very good way to conclude this amazing presentation. Thank you very much for your amazing project that triggered all these discussions. I would like to take 1 minute of your time to just give you a couple of thank you because this project, let me close here. Up. I want to mention a couple of collaborators that have made this project possible. No? So I hope that I didn't share. Thank you. Wonderful screen. Thank you. We hope that the students have demonstrated now that the capacity to this technology could to bring new architectures, but also to push more Earth architecture in this world. That we believe a lot of potential was already existing here, but needed a bit of refresh with maybe more productive tool like a 3D printers. So we didn't spoke numbers, but also more beautiful approach to architecture that a lot of people imagine as old houses, a bit blocked, something that is from the past, that is not from the future, is not actual, not modern, and probably not worth investing money. No? So that's why concrete in general is also a cultural problem, but we have to prove it. So what is interesting is that here we hope the students and this research here in EAC have demonstrated some of that. I wanted to thank some of those people around us that believe in this project and have been supporting these programs and also the research at IAC. Colette, it's a group in Switzerland that have been helping us a lot with scholarships to bring actually Africans to IAC because it was not so easy necessarily to come. And so we have 2 of our students that came from this scholarship. We'd like to thank them a lot. They repeated this year and extending to other continents as well. If there is some people watching from those Africa, South America, or Asia, check it out. Is online for the Colette Scholarship. Shameless promotion. Another group that have been helping us a lot is WASP. WASP machines. They're crazy. They call themselves World Advanced Saving Project. They really believe in these ideas of 3D printing and saving the world is this. They're doing an amazing job, but most of them is also amazing machines that we have some of them here. And hopefully for next year, We'll have also much larger scale machines. So probably with next year's 3D printing, the presentation will not happen here, but inside the building. Let's see. I see some people waiting for it. That's good. We have Julian Habitat that is not here for us in the prototyping, but in the vision of where could we apply this, that have been providing certain scenarios in the past and that are supporting to see how this is possible. They didn't bought it yet, but we hope we'll convince them slowly. And then we have a couple of other people that have helped us, Agile Escolares, that have provided us with a lot of material, especially for the exhibition, for the Terracotta Biennale, together with the ceramists, the Association of Ceramists of La Bisbal. Been an amazing collaboration to start this element. We had Smart Citizen team that helped us with some sensors, and we have the back evidently that supported us to see how we can calculate and sign those structures. But most of it is amazing people that we have below. So I will not list them all, but I want to very thank our amazing students that trusted us for these 6 months. It was not easy at start, but you made it, and we are super proud of the result, to be honest. We really like where you reached. We believe it was convincing and going there. The team of faculty also super dedicated. There's a lot of hours with us to make it happen. The team here at IAC as well was a chance to be in this environment. That is amazing. And also the jury that came today. So thank you very much for everyone. I don't know for you, but this kind of hours make me dream that technology, design, architectures can actually make a better world. And so I'm happy to dream with you. Thank you.
Yes.